Um, right. Welcome to the Composites Critical Design Review for the 25-26 season. I'm joined by many of the Composites members and, of course, substance leads Amaya and Ocean. Also, I'm Drew. All of you know me, though, I hope. Let's get started. So, going into the quick agenda for we're going to be covering today. Um, Team system goals, what we'd like to get feedback on. Some of the purchase items we'll be talking about throughout the PowerPoint. Of course, high level parameters from the system, and we're also gonna be deep diving into part level design breakdown, decisions we made, why we made them, and of course, we'd love feedback on those things. Lastly, we're gonna finish off with the research projects, and not mentioned here, but manufacturing. So that's going to be throughout the entirety of the presentation and a little bit at the end as well. Starting off with the system overview, team and system goals. So the composite system, we do a lot of the design work and also manufacturing for aerodynamic components, other components on the car that are made of composite materials, like, for example, firewall and closeouts. And of course, the main aerodynamic parts that you think of, like wings and under tray. The biggest goal that the team had this year was weight savings. This would be a weight savings year. But being the composite system, we already have pretty light components. So we are focusing instead on, along with weight savings, structural reliability. Our feedback from comp, from judges, and from a lot of the other members on the team from other systems is that the quality of manufacturing and creating things is a bit better, and validating them for design judges would be most beneficial for us as a system. So moving from 90 to 100, we've already gotten to 90, but pushing towards 100 is our goal. I've joked quite a bit about getting 11th in design, I think 2 or 3 years in a row now, hoping to push that towards top 10. With that, validating composite structures, improving consistency and reliability within manufacturing, and of course, proving that to design judges in the end. And also, I want to mention that thank you guys for, of course, like joining us this morning. I know it's pretty early; it's 7 a.m. here. I do want to keep this about 1.5 to 2 hours, but we know how design reviews go, so stick with me, guys. This is a system level assembly of many of the composite components on the car, not just within the composite assembly. You'll see a lot of components that aren't controlled by the composite system, like for example, the control arms or headrest, but we work with those systems, body and dynamics, a lot to develop these. A quick overview of some of the other parts that composites works with. First, starting off with materials integration, led by Ocean, headrest, steering wheel, steering column, panels for seat pan, closeouts, adhesive testing and materials testing, along with rod selection for many of the parts for dynamics and body. Moving onwards to aerostructures, we have the rear wing, front wing, bodywork, which consists of nose cone, side panels, under tray, and most recently aero validation, which we hope to continue with our wind tunnel tests. With all of these, there's mounting and manufacturing, which we'll deep dive into in this presentation. Main feedback items we'd want to hear about, quantifiable things that you think judges would really care about. Focusing on mounting structures. Is there anything wrong with these? Anything that sticks out to you that absolutely will not work? Structural validation. Sims testing. What more should we simulate and validate? What more should we design and prove? What more should we iterate on? Manufacturing processes. We have a lot of changes this year, and with that, is there anything that comes to a concern? We have a lot of really smart alumni here who have a lot of different experiences within manufacturing. We'd love to hear what y'all think about what we want to do this year. And of course, what would judges think? How would they judge us? How could we use what we are doing? And what could we more do to prove a better design score and cater to the judges? Starting off with materials integration. Ocean? and let me know when to click next. I cannot hear you. You might just select the down arrow next to the audio button and make sure you have the right mic selected.
Hello?
Hey, we can hear you.
There we go. Okay. Sorry about that. Yeah, so I'm Ocean, the subsystem lead for materials integration. Some of the topics I wanted to discuss today is the headrest backplate, the steering wheel, seat pan, firewall, heel pan, and pedal face. Those are kind of minor, but we'll mention them. Also the dash, steering column tubes, and control arms. Um, Yeah, and on the right is a lovely picture of all the components, except it's missing the steering wheel and the heel pan plate. I wasn't in the 000, but that's okay. We'll add it later. Yes, so starting off, so we were tasked with designing a headrest that can withstand a 900 Newton load. Um, and Yeah, so last year we had done uh just a plate with some cut extrudes, which we tried that this year, but we got a very low factor of safety and it was deforming too much. So we decided just to make it a solid plate, and the weight increased slightly, but it was kind of negligible. So we decided just to uh, go with a solid plate because we were able to achieve a better factor of safety. Um, within the reasonable limit. It's going to be attached by like two bolts with tabs on the top and two prongs on the bottom that are bonded to the plate. Yeah, and then there's some images there and a table with different laminates we tried. Um, so we had a 3-core 3, 4-core 4, and a 5-core 5. Um, we tested more just to be more conservative with our um, simulations, but it looks like we can do a 3-core 3 and be just fine. Um, Next. So for the manufacturing, it should be pretty simple. As some of the other upcoming slides are going to be wire jet, a carbon fiber plate, and with the way our layups are structured, we should be able to do a bunch of them on the same carbon fiber plate. So like the steering wheel, headrest, and a couple of other things, since it's gonna have the same like layup orientation. Um, yeah, and so we can, it should only take like one work day to actually knock out like all of them. Um, and that's the final laminate we would choose, and the oh wait, actually no, it's about the same weight as last year, with a slight decrease of 0.005 pounds, very little, but it's less. Also the part only co is going to cost like 20 bucks, which I think is pretty good. Um, yeah. I guess feedback, or what do you think? Should feedback be towards the end of like the all my slides or just the individual slides?
Yeah, I was actually just about buttons that I mentioned. I'm thinking at the end of that slide because they're pretty comprehensive with their own details in each slide, and I don't want people to forget what they're thinking about. So feel free to button like before the next slide, or if you do go to the next slide, just ask to move back.
Okay. And should the um, people watching like be writing stuff down somewhere? Or I'm not too sure how we're gonna keep track
If
of
if
it.
they choose to, I'm taking a couple notes on whatever people mention. So if you all want me to note anything down, just let me know in the chat as well.
Yeah, we will probably my guess is likely it would be good for us to like raise our hand if that's in here, which it's not, which is fine. Yeah, I agree with Drew. I think after uh, if you have like let's say we have this headrest manufacturing and then we have Leo found out how you raise your hand. How do I raise my hand? Oh God. Okay. Um, eh, if it shows that I've gotten old and not had to use Zoom in like forever, this is the answer. Um,
Well, I hope
yeah.
not to miss hands because I'm not actually, I don't see the hands being raised.
Oh, perfect.
I can see
Uh,
it, but feel
okay,
free to butt
good.
out as well in
Yeah,
case you can't.
as long as one of y'all have it. Um, but my statement is just going to be like if there's a mounting section after this where you talk about mounting, then like my only statement would be like if you feel like maybe there might be input about this slide, then just ask. Like, are there any questions?
Okay.
And we can ask at the end of every slide. Like for me, I'm going to be like, um, we're all good with stability on, non-normal impacts for this like 000 core 000 laminate, right?
Hmm. Yeah, this is kind of a over um in a large force to begin with, 900 newtons. Um,
Yeah. So the issue with the one last year was just they were having deformation concerns, but it didn't fail, right?
yeah.
Do the rules state anything about max deformation on a headrest?
I don't recall any deformation.
Yeah, I don't
Uh,
either.
just that it can't, or it has to be able to withstand
Yeah, there's a certain
like
amount of
900.
force
Yeah,
in the X direction and a certain amount of force in the Y and Z.
yeah, yeah. And the laminate we're going with is just a
Yeah, I've noticed.
0, 0.
Yeah, it's a little that's my only concern is because you don't usually see, but I guess you can do that. Why are we seeing the tiny weight increase? Are we using a
Actually, it was a
different?
weight. Oh, wait, no, it was a weight increase. That's right, it was a weight.
Yeah, but it's like
Oh,
seven
it's
tenths of a thousandth of a pound.
yeah, it's because last year we had like part of it like it was cut extruded, so there was like it's kind of like a T with the carbon fiber in the middle, but it was like very little was cut out. So I think that's where the main change came from. Um,
Oh, okay. So this technically has lower like surface area.
no, this have this one, the new one has more surface area.
It's a bigger part, right? So what you're it has less
Less of what?
fixed headrest. Oh, okay. Thank you, Ryan. Yeah, that will do it. Yeah, having a fixed versus adjustable will that will do it.
Ah,
Okay, cool. Yeah. So like the headrest plate, right, on an adjustable one has to be the the size of your adjustability versus a fixed headrest where um it no matter. I think the headrest has to be a little bigger for the fixed if the rules maintain the same. Memory is leaving me. No rules for failure by fracture, anything, but it needs to be able to withstand a 900 newtons. Oh, the fixed is smaller. Why would they do it that? Okay. Um, okay, cool. Yeah, no, looks good for me. What's your safety factor?
it was Drew, can you go back one slide?
Sorry, it's getting
It
computer slow.
was 1.356.
Mm,
That doesn't sound good.
what was last
The-
year's?
Here's actually I might be able to pull it up. Nah, actually I don't know.
Ah, here's going to be the lesson for this design review. Make sure you have if you're comparing parts to last year's, make sure you have last year's safety factors.
I don't it wasn't well documented. Or at least I couldn't find
Okay.
all
I
the if
okay,
there
that's
was factors.
understandable. That's understandable. It not being well documented is not a
Yeah. Can we go back to that other
uncommon.
slide real quick? Or the previous one? Like the deformation was around it's like or what we were seeing in the sim was like 0.0436 inches. And I thought that was kind of low and
Yeah,
kind of
just
acceptable.
yeah. I almost wonder if we should look at, do you have the material specs that y'all are using for your simulations? Right, these are your
I,
first simulations, and material specs are super important to
yes,
composites,
Yeah,
and
I
it's
have
kind of
those.
hand wavy because I know y'all haven't done any testing. So
exactly. Like I think that's way too low of a safety factor. We haven't done any actual
Chime in. I see your
testing.
hand.
yeah, usually our minimum we're sitting at is two. Usually
Yes.
we don't want to go anything below two when we don't
Oh, for
have
safety factor?
yeah,
This is
when we
like
don't have material testing.
industry level like safety factor where they like do like extensive testing and like they know that the airplane's not gonna fall out of the sky, right? Like yeah, so like we should definitely be trying to aim for two. I think one suggestion I have for this slide, Ocean, is if you're gonna show FEA screenshots, try to make it clear where you're applying your loads and your boundary conditions. I can't
Oh,
really
I
tell.
have other screenshots that I didn't
Okay,
include.
okay, no worries.
Yeah, we
Um,
have a
Yeah,
whole
the nice
PowerPoint presentation of like one of our members did it, Jacob. He did a pretty good presentation of the of like how he defined his boundary conditions. Like at the it was there was two tab positions kind of like at the top, circ kind of like roundish off the end.
yeah, I saw the bolted holes, yeah.
Yeah, actually, can you go to the next image? It's a little bit more clear, I think.
Yeah,
You
the bolted
kind of see
holes
it
in the
there.
slots.
Yeah.
yeah, I see the slots on the bottom. Yeah.
Yeah, those aren't, it's not slots, it's kind of like lines over it, and that's kind of how it was uh done in the lines at the bottom, yeah.
Okay, yeah. Yeah, with like funky parks like this where we're not really, right, like you have to convey the information to us, right? Like I'm not trying to babysit y'all every step. So I don't know what's going on, which is exactly how it should be. And so, but that does mean that like y'all have to convey the information that I'm not gonna know, right? So
Okay, so
y'all could be fixing something like if the bottom here is bonded, but you're like fixing it and you're not putting it as like a rigid joint with a failure stress, then you could be having an issue, right? Like there could actually, you could be seeing failure at the bond, um, but you don't know because you just fixed it. And you're not like, you can note it as well. You could see like what amount of stress is going through that location. But like, you don't know. Um, but
gotcha.
anyways, yeah, I would say, we never did anything below a safety factor of two on any composite part without running through the full rigor of composite testing, whether that be push rods or that be tie rods or that be wings or, anything. We wanted to make sure if we're running simulations, then we know it's at least a two until you have material testing data.
Gotcha. And yeah, and later on the slides for like our research projects, we have a material testing plan for the control
Right.
arms and like 3-point bend test for different like layups, like three core three for or different orientations as well.
Yeah, I'm not as big of a fan in doing like sandwich panel testing, um, just because I don't entirely like that means that all you can use is a 3-point bend on a three core three that was manufactured, February 10th. Right? Like
I see what you, yeah.
that's basically what that testing plan will create. Um, I don't expect you to do something like what like Tesla or Boeing or GM, I don't expect it to be that rigorous, but we can at least follow general material testing guidelines that do exist. So, which usually just state like you test the ply independent of its direction and independent of any core or additional materials.
Okay.
Yeah. Anyways, let's
Yeah.
Leo, you got anything?
Yeah, no, I think that's fair. Just trying to get like a solid material property so you can update your FEA. I think I was telling Maya in the past, like having these models are still really good. As soon as you do your testing, just plug and chug into your sim and see how things change. But for now, yeah, try to aim for a higher ply count. And I guess it's hard to use deformation to quantify this kind of stuff, right? You mentioned like 40,000 isn't that much, but it's like I guess what is or isn't that much in this case. Um, like I don't think there's a really easy way to quantify. You should definitely be just looking at factor of safety when it comes to these type of things. And in terms of like for aero, like yeah, of course we care about the deflection a lot more. But yeah, that's all I have for this.
Yeah, yeah. For Arrow, like we would care about deflection, but the reality is until Arrow gives us a spec on deflection, we shouldn't care that much about deflection because they haven't given us, well, how much deflection is bad
Yeah,
until they give you a
exactly.
spec. Until you give, right, like, you know, the frame could, you know,
We'll get there.
like,
We'll get
yeah,
there.
yeah,
We'll
we'll
get
get
there.
there.
Yeah, we're getting the
Anyways, yeah, we'll get
arrow.
there. But yeah, go back to
Barely
the
ahead of
previous
us.
slide.
Let's go.
All right.
Yeah, go back to the previous slide. How much? Okay, that's 0.374 pounds. Okay, so we're looking at a 1.4 pound weight gain. Okay, God, that's a lot of zero ply.
All right.
Jesus. Okay. Yeah, zero point 0.3 inches. Okay. Yeah, I would be more comfortable stating with a factor of safety of 2,
So aiming for like
unless
a 5.5 unless we validate it further.
unless you validate it. Now you could validate it by like creating a jig that mounts into the instrom that then you apply the 900 Newton load on a thing, and if it survives the 900 Newton load for a certain amount of time, then you can say that, it's validated. Like you could physically test every individual part with mounting jigs, but that's a pain in the butt. So, okay, cool.
Cool. All right. With that said, I think we can move on to the next steering wheel. Yes. Okay. So the steering wheel, we had three different tests to do. A 150, 150 pound push-pull test, so that was 75 pounds at each side, and a 150 foot-pound torque test applied kind of at the inner thumb grips and the outer side of the wheel. I showed that picture up there in the top right, kind of show you what I mean. And also um a drop test to not exceed like 300-pound force. So the two different laminates we were looking into were a both 3-core 3, but one was with a 45-degree um, ply instead of just straight zeros. And we found that the the just the straight zero plies was a lot stronger in both just 3-point bending and torque, which was I thought was kind of odd, and I'd like kind of like your feedback to why that might happen for if you guys know um for the yeah the t torque.
It's stating that your max deformation is larger in the
Oh,
triple
that should
zero.
be min. I
Okay.
don't know why that says max. Oops.
Okay. Yeah.
Wait, no, no, actually, no. Yeah, I think that is max deformation. Yeah, I thought, yeah.
So my problem with how we run Sims is like, so you did torque like you're rotating a steering wheel like you're driving, right?
Yes.
Did you do torque in the X direction? Like they're pushing one hand forward and one hand back?
I kind of did it with like so if you see like the top right picture, I did a force acting at like the kind of like the
Yeah,
top
you have one force, you have like
one
the
acting in the negative Y and then one acting in the positive Y.
right. So I'm saying, have you done one where you have one acting in the positive Z and one acting in the negative Z?
Oh, kind of like a push and pull test.
Right. Because, okay, here's the problem with people. People suck, right? Because people are going to load your parts in every single way. Like, this is what makes Ergo hard that most FSA teams tend to kind of miss, which is why like their Ergo parts are always super beefy, is because the reality is people suck. And people are going to load your parts in like atrocious ways.
Mm.
Um, have you looked at core crushing, right? Like the
Um,
driver's going to be squeezing this steering wheel. Are you going to have core crushing? Because obviously it looks like you're using core. Because it looks like
yes.
you've gone with a flat panel steering wheel, which will be another topic of discussion. When I assume we look at a comparison slide between all of the versions of steering wheels we've had in the past.
Hmm. That would be a good slide to have, wouldn't it?
Oh my goodness.
Uh-huh.
That's the very simple requirement we had starting this. Yeah, okay. Um,
Yeah.
yeah, and once again, right, the
I
triple
only had a
zero
slight
core
comparison of
still is not it's close to the two, it's close to the factor safety of two. But yeah, I'm not seeing all of the possible forces a driver could load into the steering wheel. I'm
yeah,
not
I could
seeing
add like another sim or like kind of another
Yeah.
box for like
Yeah.
the
Well, you
positive.
can make these answers, you can make these answers, if you leave them all in this same direction, then you can just say like you could just like take one of these axes and just like leave it on the corner and say like all pictures are done in the same reference, right? Like, and that like cuts half the photo. Because I don't need to know that you're running it in ANSYS 2024 R1, right?
Oh yeah,
I,
some of
I
these were
don't care that
previous
much.
screenshots that I had.
That's fair. That's fine. But yeah. Yeah, for ergo parts, you need to load it in every single way that you can think that a human can load it, or you have a part that's so beefy that there's no way for them to destroy it, right? Like the SMC steering wheel, right? A part that was so indestructible, there was no way they could destroy it.
Mhm.
Um, so yeah. Anyways, that's all of my statement for this is I think you need to run more information before you can be really confident that a driver's not going to destroy this. Especially since it has core. Especially
Mhm.
since it has core. They're gonna destroy it.
But yeah,
Yeah,
Drew,
what
can you do next slide before we because there's another steering wheel
I
slide.
think yeah, I think
okay.
yeah.
Yeah, so this is the manufacturing, or it's similar to the headrest, just kind of water jet a plate, and for the handles we were thinking like a 3D printed silicon or or wood. Um,
What would?
I don't remember the kind of wood name.
Ah, welcome to engineering. What
Yeah,
would? 3D print wood?
no, not 3D print wood, but I forgot to grab the type of wood, but there was an
do
Instagram
balsa.
reel. There's an Instagram reel I saw. I know it's terrible, but
Do balsa. That's your answer is do balsa.
oh,
Balsa's super light.
oh, that's the wood.
Yeah.
Oh, okay,
Balsa.
perfect. I
Yeah,
will look
slightly
into that.
balsa. 3D
Um,
printed silicon. What do you
yeah.
mean?
Um, I can't remember the exact PLA or not PLA, but the silicone material.
The
But there's like,
TPU?
it's not the traditional like.
There's just always we did 3D printed silicon grips once, and the like that's what made us do the SMC because the driver's response was these are pieces of crap. Because they
Yeah,
were just falling apart. They looked ugly. Yeah, it was TPU. It was
I
awful.
don't.
They
Yeah, I don't
were
think it was
ugly. They
TPU.
fell apart. They were just, we had to replace them because they fell apart.
Yeah, or
And
like,
we didn't drive that car very much. That was bad. We
yeah.
didn't
Do you know
drive
those
that
like
car
other
very much.
printers that are like the where you like fill them with liquid and then like it uses a laser to like
Yes,
I was thinking of
SLA.
that kind of like silicone.
Yes, you can use, they have a rubber, they have a rubber.
polymer or some
Print.
kind of
I've printed
compound
with
in
it
there.
before.
Yeah, and so that's kind of
It's
what we were thinking. Not TPU because what happened
individuals'
with
hands.
Panda.
Yeah, that also sucked. You're correct, Ryan. But they also fell apart, which was also a huge complaint.
Oof.
Um, which is why we went to a composite that formed the outside rather than. But you film it with grip tape, right?
Mhm. But with that,
No, not for Panda. Panda was a TPU with no grip tape exterior. Oh, this year. Pet G with grip tape wrap.
oh, what?
Yeah. Okay. Hmm.
Hmm.
Okay. Yeah. Still, those are both hard materials. You're going to start to like compress core because what you're going to have is you're going to have loading through gripping, right? You're going to have loading on basically what is the outside squishing in. And so you might run the risk of crushing the core on the outside. And the moment you crush that core, you started a crack delamination between the core and the ply. And now that's going to shoot across the composite because you have no like I'm assuming you have no composite actually going in between the forward and the back side of the steering wheel. Is that assumption correct?
Uh,
Like it doesn't
sorry.
actually look like how this picture is. There's core being visible.
Oh yes, sorry. It wasn't in CAD. It didn't have
No,
the
that's okay.
carbon fiber. Yeah,
To do
yes, it says
that, to
core.
do that,
Yes.
Ryan will be very upset because now every single part is three parts.
Yeah, it sounds
So,
about yeah.
yeah,
It's
um,
actually not like this in the CAD. I just did it like a quick surface from like a
that's okay.
read-only part, so just to get like the kind of basic idea. But yes, this and the headrest were have core in them.
Yeah, I'm less concerned with the headrest because the reality is, like, other than the rules, we really don't put that much force into it in like shear.
Yeah,
Um, unless y'all are doing something really funky. But for steering wheel, because we actually do, cyclically load this thing, since you have no composite, going from the forward side to the aft side, you have no control on, on your shear, interlaminar shear between the core and the skin on both sides. You have no control and you have no stress sharing unless it goes through the core. So the moment that you have an interlaminar shear start crack progression between the core and the skin, it will start to progress through the part, and then the part's just done. Um, so I would just be very mindful of that. And it's the reason why, in the past, we never touched a flat panel steering wheel because just from like a general engineering theory standpoint, it's not going to be the best, right? Like mass moment of inertia is a thing. This is not how you get the biggest mass moment of inertia,
yes,
right?
yeah,
And your failure point is going to be your composite skin to your core shear. And we don't have data on that. And are you running interlaminar shear properties on your sims? Like, do you have a layer between every single ply? I'm assuming the answer is no.
Wait, I didn't quite catch what you said.
So there's a way you can do it in ANSYS where you run, like, you know how in ACP, right? It has every material has a layer, and then the core is one big thick layer, and then every material has a layer.
Yes.
So there's also a way to have interlaminar meshes that put a mesh in between each ply to replicate what it basically is just pure epoxy. And that's how you check for interlaminar stress. Now, how we get away from that is we just, don't. And we just have a high safety factor because we also don't have the data for that. Because every single ply and every single different way that you manufacture the composite, whether it be wet layup or pre-preg with an autoclave or pre-preg with an epoxy adhesive layer, they're going to have different interlaminate shear properties between the core and the skin. So to do that, it's really recommended to do physical testing. Now the physical testing is easy, but it is something you have to do.
Hmm. So would you say like and like in a general composites standpoint that like a safety factor like since there's all these factors at play, we always want to aim like above two?
Yeah.
I know it's kind of like hard to generalize it, but
Leo, what's your thought? Because I would almost be concerned for ergo parts where you don't know how it's loading to maybe go above two, but like it's like definitely a minimum of two. What's your thought, Leo?
Yeah, no, I agree. There's just a lot of uncertainty with how this thing's gonna get loaded. One thing I wanted to mention, if you go back to the other slide, is you have a very specific load case on the handles of like how you have two main load cases, but I would also say like I mean the driver doesn't always just keep their hands at that spot, right? Like do they ever grab the bottom? I was never a driver, so like is there ever
Yeah,
uh,
they have more than two fingers.
yeah, they can grab the bottom of the wheel, right? Like they don't just like hold that like top section the whole time and there could be like unsymmetric load cases as well. I think that's why okay, they don't. I don't know, right?
yeah,
But like if they
I don't think the rotation of the wheel when you're turning is like that. We don't need to go that far to like put your hand on the bottom of the wheel. I could be wrong.
Yeah, but like if you go back to the previous slide, that way we can have a visual
Yeah,
example of what Leo's talking about. Drew,
Drew.
Drew.
Previous
yep,
slide, please.
Thank you. Okay, so
Um,
like below where you have the top cut
oh wait,
out,
sorry,
right?
that's actually not a most current image. Now
Oh
that's
dear
funny.
God.
Yeah.
Come on, guys.
I apologize. Yeah.
So
Yeah, no,
don't
I
grab the
actually
real
did
button. Yes,
account for
yes,
like
Ryan.
some
Yeah.
fingers at the bottom and like kind of like so like the red kind of extends down to that past that center hole. Um kind of to
Ryan's
where that line is.
105 degrees plus or minus 15 degrees.
I'm curious. So you like instinctively like I'd want you to go for the 45 ply case here, but like I want to hear your reasoning behind doing the simulation for that. Obviously here it looks like it's not as good, but that's just because of the load cases you chose. Right. Is there a specific reason why you wanted to try the 45-degree plies here?
Yeah.
Or
Well, honestly, we tried a bunch of them. I didn't include them all, but we had done like 4 core 4, 5 core 5. But we were just curious to see how different uh like orientations would actually affect the this part. And yeah, it was kind of weird. We thought the like having a 45-degree ply would increase our safety factor for like the torque test, but it didn't. And I think why that was is because we like the plies aren't like bonded together in like the most or like they don't sink into each other as well as the 000. But actually, I'm curious to hear what you guys.
I mean it's because you're not twisting the plate, right? That's the only like that's how you the 45s would actually help. Like you only have one case where you're I guess I mean twisting is like in plane, there's no in plane torsion of the plate. You're just you're turning the plate about the mounting, right? And then you're just bending it. So like the 45 isn't going to do anything for either of those load cases. But like if you do have any like in that case where Wesley said where you have like one arm pushing in, one pulling out, you could have like a I guess an in-plane torsion, and that's where the 45s would help a lot. Um,
Oh,
Potentially. I mean,
Yeah.
I just don't know how uneven the load cases are, but I think realistically in real life, like I don't think you're gonna have a perfectly symmetric load case from the driver while they're like in every single scenario. But like that's what makes these like super difficult to analyze, which is what Wesley mentioned. Um, but I mean, I think it's a good start, right? You got the two main load cases here. I think this is all the basically all the analysis that was done last year, right? Or the year before. So yeah, I think that's all I have to say about the steering wheel.
Yeah, and Ryan and Leo, of course, who are talking in the chat, did bring up another good point that you don't also have here that will affect your 45s as well, which is the fact that when the drivers are pulling the steering wheel off
Hmm.
and putting it on, that's supposedly like 150 pounds. So, like, just note, right, that the drivers are going to be pulling, and the reality is, one person's arm is usually stronger than the other. Um,
Oh man, that's real nitty gritty.
there's a well, but like the welcome to the nitty gritty of ergo, right? Like if you
Yeah.
want to get nitty gritty and you want to start doing simulations, then you need to be aggressive. Then you need to be aggressive uh, with your simulations, and we want to make sure that like we cover, whoever's the strongest person that you could possibly think of trying to abuse his car because you don't know we might bring this to an event and a body lifter comes or whatever, right? We're there's like these ergo stuff we need to sometimes account for the fact that this car will see the public eye. So this gets it back into the safety factor conversation where it's like, well, for ergo parts, you might need to be, closer to above 3, while for aero parts, we might be able to, sneak ourselves down closer to 2 because there's also the other reality that like aero forces are not realistic.
Hmm.
There's a safety that like their forces are like the best possible in the world they could possibly be, and this is the max. So there's a conservative on top of that as well. Um, so yeah, okay.
All right, next slide. Yeah, cool. Okay, so these here's the seat pan. I condensed the slide to be design and manufacturing. So for this seat pan, we set it up to be like parametric CAD. So like when we adjust the frame, it'll just auto fix the dimensions so we can have the it saves us time. And we wanted to increase the ply count for the upper small or no, the lower, yeah, the lower one, so aka the big plate, because last year we saw crushing and core failure um, uh, of when we were stepping in and out of the plate at unveiling. Part of that was also probably due to small tab sizes, but I think to be on the safer side this year, we increased the uh, surface area of the tabs, as well as increased the or added up 2 plies, one to each side for the lower uh, seat pan. And the upper seat pan stay the same of a 3-core 3. Um, yeah, and also I have the chart at the bottom for the comparison for last year. We did gain a little bit of weight for mainly because of the lower seat pan and the extra plies, but be it should work out better for us so we don't see crushing like we did last year. Um, yeah, and same manufacturing method, just water jets and plates. Um,
Yeah, have y'all looked at the sorry, was I messed up my Zoom somehow. Um have y'all looked at uh Panda's mounting tab size?
no, or at least I
Okay.
haven't personally.
So like that was the last time we did, large, math on CPAN. And it was quite an extensive amount of math and simulations. And we like calculated what size the tab should be, and I remember doing it. you know, like you're really playing with the science.
Yeah, I think Clayton might have looked into that with
No,
those calculations earlier this year. I don't think he's here right now, but
he's not here.
I
No.
can reach out to him and see if he did some calculations of like what you're referring to.
Yeah, I would just be like right? Like it makes sense why the ones Clayton did last year failed, right? They were super tiny. They had this huge fillet on them, and you were compressing the core last year. And it was cut short, right? So you didn't really have, but the whole statement is you don't have you have a small amount of cross-sectional area pushing and creating a moment arm on the skin, right? Almost think of the skin as its own independent beam with a light spring on the end pushing back, right?
Hmm.
And the moment that it bends enough that that light springs tiny little, fracture force in compression fails, then immediately you have delamination, and then it's the same conversation we had with the steering wheel. So there's two ways to do it, right? Either you increase that surface area or you start to add, something that has a higher compressive stability within it. So that could be, it could be something as easy as increasing core density. It could be something as, not as easy as adding an inner ply, or you could do something like what Ray and I did, where we actually added a piece of carbon that wrapped around the edges of the seat pan. And the other reason to do that is also that any exposed core material will degrade with exposure to water. So if it rains, which it does, or you sweat, which people do, and it hits the core will degrade. So yeah, be careful.
Oh,
Like in industry, we have no exposed core ever. But
what solutions do
whether
y'all
that
offer
be
then to like
automotive
kind of
or
cover it?
yes.
Is like, do you use like a tape or a paste?
Look back at go find Panda's seat pan.
Oh, do we still have that?
Should be attached to
Ryan,
Panda.
do we still have Panda?
Yeah.
Hmm.
Yeah, it's a pickle. Yeah.
Oh, okay.
Yeah. Look at Panda's seat pan or Panda's firewall or any of that, right? That was our first year we did pre-preg and we did a lot of preventative measures. And as we've backed off of our preventative measures, we've seen some of those problems come up, right? The preventative measures that, Ray and I did, Ray and I and Leo and Noah and Alex, those preventative measures that we did, um, you know, as we've backed out of them, have come back in full force. Um, so yeah, we like did a tape of carbon around the edge and then light cured it without a bag. And it's just something that's, and it's a little structural, which is beneficial. For the tiny mounting holes, it doesn't really matter. The bolts should seal. Make sure you use a rubber washer for any of your like mounting locations if you're going to bolt anything through anything that doesn't have a good surface area or doesn't have like an oversized washer on it. And then for these, what I'm assuming are drain holes, I have no clue what they are for.
Oh,
Um, just put a little bit of of epoxy adhesive around the edge. It's preferable if it's urethane, but it doesn't matter. Um, cool.
cool. Uh, Anyone else have any other input to add to that?
You also don't have your ply schedule on here.
My what?
Your ply schedule.
Lie
It
schedule.
just says three core three.
Oh,
Three
it's
pieces of fiber.
yeah. Usually if
I assume it's 0 45 0 and then 0 45 45 0.
yes, it can be. Uh, yeah, I had a note actually in like my separate slide doc where I had the notes for that because it was just too much to put in that one line, and I did not add it, unfortunately.
Okay, and then I'm assuming these are two separate pieces.
Yes,
Well, okay.
yeah, and each one has a different laminate. So,
Yeah. And
um,
the lower one is the tiny square we're looking at.
no, actually, the lower one is the big one.
Okay. And the lower one is where the driver sits.
Uh, yeah, so like the Or
But
the big one is like where the firewall kind of goes. That says the back of the car, and the smaller one is kind of towards the front of the car. And the front one is kind of like right underneath the steering wheel.
okay, why not for seat pan? We use forward and aft.
Wait, sorry, what was that? Oh,
Why
forward and
not?
aft. Oh, my
Yeah,
bad. Um,
seeing
yeah,
as
we're gonna add more sections. Actually, we could correct that naming convention now. Um, because yeah, it was kind of engulfed into what's pedal box heel plate. Um,
oh well, then you can also segment it. You can segment it like you can say like, this is forward of hard point, aft of hard point, aft of driver seat, um, aft of firewall, right? Like, because I'm assuming you're not going to have like upper and lower makes me sound like there's one that is drastically higher than the other,
yeah,
right? Like think firewall, right? Like think
I think in the
firewall,
cat I
right?
had it as top and lower or something. It's something bad. There was like two different ones. So
Okay, fair enough. Cool. Yeah. Just was
fix my naming convention.
was confused by naming convention.
Yeah. Uh,
Okay, cool. Thank you. I assume safety factors next slide.
no. Oh, I don't have safety factors for these yet.
Hmm.
Hmm.
Okay.
Yeah, anyway. Um, yeah. We have two different firewall. Actually, is that all the questions for the
That's everything I have. Leo?
I'm good.
Cool.
Okay, cool. Uh, firewalls. We have two different ones, the upper and the lower. So the upper has taken new form this year, and it last year we had did a bench sheet metal plate. We cannot do that again this year. Um,
So you understand this will have to be a pre-preg mold then, right?
yes, so this is going to be a PLA male mold to make a fiberglass female mold to where we could lay up this part or the carbon fiber on. Um, and we
Hmm.
should get the nice surface finish on the outer side, which will make Aero happy for their
What's
aerodynamics.
what's what's with this negative contour that I see in the front?
Um, it
It's like sweeping up
yeah,
and then has this quick radius turnaround. Um,
yeah,
yeah.
it was some Aero took charge on the
It's because of the
design.
headrest, and also, it's like almost like an inch of radius.
So what's this? What's our ply count?
It
Three.
should be about like three.
Okay, what is on the female? So on the top side, the visible side, the
Yeah,
female
so the
mold
side that's
side,
visible right now will be the shiny side. It'll
what's
go
the
into
minimum
the female
radius?
mold. Oh, what do you ask?
What's the minimum radius?
It would. Ooh,
Because there's a couple areas where it's like you have a good you might have a good radius on like this forward flat side, but then it gets kind of cut away by this odd contour, so it makes me unsure whether or not you're conforming to that radius, and I don't also know what that radius is.
wait,
So
which radius
I
are you looking at?
the difference is 0.02 smaller than on this car. Panda is 0.5 versus. Okay, cool. Yeah. I know last year's car was like 0.12 or something. So like that didn't help. So perfect. Yeah, half inch tab sounded about right. Yeah, we made half inch tabs. Yeah, no, Ray and I don't like funky numbers. We're boring people. Um, no interest. This is why I hate doing Zoom. I don't get pointer rights.
Can you direct kind of like which side of the image?
Okay.
top left,
You see
bottom.
where this silly concave shape is, right? Looks goofy.
Yeah,
Yeah.
right. Yeah.
Yeah. Okay. You see the front where it like radiuses to this flat side? You see how that's non-continuous radius out towards the edges? Like I can tell with how the lines are formed that it's a non-continuous radius, right?
Mm-hmm.
So what is the minimum radius? Because, right, the prepreg can only go into, X minimum radius. And you're making it not any easier. Have y'all gone into the 3DX that I know you all have access to and gone and tried to do a ply contour analysis on this part?
I have not personally.
Cool.
Um,
Yeah, so like y'all should do like apply stretch analysis on this because this is going to be a very like you no longer have your people who have the expertise in hand laying up prepreg without the need to like look at those type of analysis. Like y'all don't have that anymore. Unless y'all have been laying up prepreg parts for the whole year and I'm unknowing to that. Um, y'all don't have that. So in length.
so we'll have to look into that then.
Anyways, yeah, so do look into that because this is a really funky shape, right? Any of our funky
Yeah.
shapes, you should start to look into that. And it's great. The judges will love it.
Mm-hmm. Cool. And the lower firewall, that should be kind of just another plate layup with the water jet.
Yeah, and
Um,
Ryan, I think it was also where the welds were because I think on Panda we had them weld at the bottom of the tab, and then because I remember Pandas also being kind of short, but then I remember on Raccoons, I believe it's welded on the top, which technically makes your contact area smaller.
It didn't matter. The seat pan like was too small.
Right,
Like
right, but
it
I
did not
think,
contact the
but
weld,
right, right,
and it
right.
was welded on the bottom. I welded it.
Okay, I thought I remember seeing it on the top. I don't know. It's been a long time. Anyways, now that we've moved on, cool. 300 water jet plates. Have you done an analysis on this firewall for putting it in?
um, I have not.
Because you have some really like negative
Upper
looking con for not for the upper, for the lower.
lower is fine. It's three part. It does interface fine. We've done it.
Oh, it comes that those three parts come apart.
So the wings are what interfaces with the frame tubes, such that there's like no gap, and then the middle part is the only thing that actually comes out, and that interface is on top. So you're looking right
Oh,
now. You're looking at the back of it. I can
okay.
send you a screenshot if you really
No,
want to
that
see.
that nope, nope. I'm good. Makes sense. Yep. It just looked like I wasn't sure if it all went in as one. Usually, we
Yeah,
usually have the firewall as one part.
yeah,
So
yeah.
okay,
It's
Probably
that
three
didn't try to
part for
fit a
changes.
ceiling.
screenshot. My
That
bad.
changes good. No, you're all good. Change is good. That change is good. Um, yeah, I agree with Leo. That is very cool. I like it. Just make sure that they're still installable. Um, just that's always going to be a problemo. Um, and I think there's a way to do it in 3D experience. There might not be. I think you have to do it in CATIA V5 or maybe in NX. I don't know. I would ask Liam and see if he can do it in NX for you because y'all don't have V5. Okay. Um, 3 core, 3, 4 core, 4.
Yeah, because the lower and the middle and the sides are for the lower half are going to be different laminates.
What is your zero direction on the top? I'm being finicky.
These were all I had all at 0, 0. zero, core zero. That's kind of why I simplify it.
Right, but like where do you start that initial apply placement?
Oh, I
Right?
was thinking,
Like look at this really funky shape. Now what is zero?
I guess that's fair.
Because where you start your zero ply, it's going, that's why I'm saying do the ply, analysis, like the fiber direction change analysis. Because it might be zero on top, but then it's going to be like plus or minus 10 degrees on the corners, and then it might be plus or minus 20 on the bottom. And like prepreg can't stretch, right? It really does not like to shear. So just be careful.
Yeah. What would be
But
your recommendation if like to follow like the long lines, kind of like the inside lines, because it's kind of like parallel with the outer edges, but then it would kind of get weird at the bottom with the curve.
I don't think you're going to be able to do this as one piece.
Huh.
Like, I don't think you can, I think there's too much contour change throughout it that you won't be able to do this as one big piece. Like it's gonna like even the even the upper firewalls that we did in the past, I never did them as one big piece.
Oh, no, I was talking about the lower,
Oh, the lower, I don't, what's the
like the corner
problem?
pieces.
The edge pieces?
Yeah, I was that what you were
No, I'm talking about the upper. No, I love how the lower firewall works. That's great. I love it. It's awesome. Wrap
Wesley,
the edges in epoxy. But
for the
like besides
upper,
that, I love the lower. I think it's fucking awesome.
Wesley, for the upper, would you think that like a fiber sim on 3DX could tell us how to best cut the plies? I remember you were talking
It
about that
it'll
before.
it'll give you ply shape. Like it will, you could print out of paper like a DXF cutout and then cut the plies perfect to shape.
Yeah, I had like another ap approach that I was thinking. Like I was talking with Drew about that and using that software, or I think yeah, I think it was that software. But also using like painter's tape to after you have your initial mold, just put painter's tape all over that to kind of get the shape. Then peel off the painter's tape, or actually when the painter's tape is on there, you like take a marker along the edge so you get the shape. But then after you peel it off, you have it like as a flat 2D shape. And then you can
It's
make a
not going to
template
form
off of that.
2D. I promise you. I've done it. We've tried.
Now,
It's not going to be 2D, right? Because some edges are going to be longer or shorter than others, right? Because what you don't count in that is the fact that you're going to need to splice the ply.
oh yeah, with like kind of like holes in the middle so it can kind of
Well, you're going to need to make
bend.
darts, right? Like you're going to have to cut the ply to let it become smaller on one edge and larger on the other, right? Like think of like if you try to take a piece of paper and then wrap it around a sphere, right? It's going to create all these little like peel up points, right?
Yeah,
And you're going to have to cut those to make it form closer to the sphere. And we do the same thing, and those are called darts within a composite. It's called a dart. And actually, the
darts.
function within the 3DX is, FiberSim is the name of Siemens software, but the same kind of thing within 3DX. I believe they also call it darts. So, um, yeah,
Well, thank you.
yeah. Cool part, though.
We'll see. We'll see how if we can make it work.
Yep.
All right, next slide. Oh yeah, so these are kind of two easy layups we can do. The pedal face is going to be like just a small sheet metal piece, bent kind of like what we did with the upper firewall. And the heel plate's just another traditional plate layup. Yes, and three core three, it would be the same orientation as like the other lower firewall, 045 0 core. Well,
Yeah, I agree, Leo. I like your comment. It is a pain in the butt, and they can't do
sorry, my
darts.
mom was talking to me. What was that?
So, just Leo said something in the chat, so it's at least recorded.
Oh, oh, okay. Flatten surface.
heel plate. 2-ply. Is there anything underneath of it?
Oh wait, oh shoot, that's not correct. It should be three core three.
Okay.
Yeah, no,
For the
sorry.
heel plate?
Yeah, for the heel plate. So that bottom plate on the bottom.
That doesn't. How big is this heel plate?
This I
What size are those holes?
those holes kind of like they go over like the corner or underneath the pedal box. Oh, where you going, Drew?
My bad.
Yeah, they kind of line up
They're
there.
just like 1/4 inch holes or something?
I don't have the exact dimension right
Okay. I'm
now.
just trying to get a reference because I have no fucking clue how big this is. Okay. Uh, does this 3D part have core in it? It just looks like it's just solid laminate.
Yeah, I was planning on core.
Okay. That 3D part just looks like it's only solid laminate.
No, yeah, it is because I didn't have the
Okay, you haven't
hole.
updated the picture. Cool.
Yes.
Picture not up to date. Yeah. For just general etiquette on like these type of slideshows, whether you're here or you're in the workforce, um, do put like note picture not up to date, right?
Gotcha.
Like just those simple, tiny little amounts of wording just helps us as outsiders understand what's going on. I love that there's pictures. I've said this before. I'm a big pictures person,
Me too.
but your pictures got to be, got to know what the fuck's going on.
Yeah.
Um, Accelerator and brake.
Oh, those, yeah, like the
Brake.
accelerator pedal was kind of discarded. We did a bunch of calculation, and it just turned out to be too heavy for a carbon fiber, and it's just way lighter with
Yeah, because what? That's sheet
metal.
aluminum.
Yeah.
That's just bent, just press brake
Yes.
bent.
Yeah. Yeah.
Yeah, yeah.
Ye-
Well, yeah.
Yeah, it is what it
Okay.
is. But we still got the brake
Versus versus
pedal
three
cover.
ply. I guess your concern is the moment that the driver, like, if the driver hits max travel and then tries to push more.
Yeah, I couldn't quite
Yeah.
remember. I thought it was like one or two ply. I think it's two ply for like the flat ones last
And
year.
that equaled the weight.
No. The weight was done for the pedal face was just three ply.
Well, I mean for the accelerator, but we're getting off topic. Okay. But sheet metal manufacturing time. Yeah, it's quite short.
Yeah.
Um,
Oh, actually, for feedback, would you recommend upping the ply count for like the brake pedal face instead of three?
yeah, people suck. Like you gotta expect that your driver, when they're getting in the car, that they're gonna push on those tabs, right? Like that they're gonna like load them in weird, funky ways, right?
Hmm.
And it's easy to like, and I assume it's a female bent sheet metal plate, or it's a male mold. Sorry, apologies.
What do you mean?
Like the bent sheet metal plate is going to go on the inside of this brake pedal face.
Wait,
The brake pedal face
I'm
is a U,
confused.
and the mold is going to be on the inside of the U.
Oh, yes, yes, sorry. Yeah, the nice side would be the where the foot is going.
Yes.
So it'd be a male mold. Uh,
Yes.
yeah.
Yeah, luckily that mold is you can always make another that's thicker.
Okie dokie.
Okay.
Moving on. Oh yeah, we're getting to the end. So steering columns. The steering column, Zach, I don't think Zach's here, but he did a lot of the research and we kind of guided him with the what kind of tube selection we'd want. So for since the steering column's like pretty much purely in torsion, we decided to go with like a filament wound tube, which is this,
Mm-hmm.
and it shows the pros and cons of each tube. Um, yeah, so we went with filament wound for torque. Oh, my internet's unstable. That's not good. Uh, so yeah, this was the tube we found. 35024 filament wound. It's about like $91. Um,
Hmm.
yeah. What else?
I don't trust filament wound
Oh,
in this
really?
application. Well, you can't run. What's your safety factor on Rockwest's stuff?
I didn't run the calcs. I think Zach
Do
has
you
that
have a
in,
safety factor?
not in the slides.
Zach and I
Oh,
run a calc
Yeah,
like
Z-
honestly a couple months ago, if I remember.
Ryan, what's the
Um,
safety factor?
I'm checking, but usually Zach ran to is 1.5 or 1.75.
Okay, I
I'll
would
double
go
check.
higher. I would go higher. You always don't trust what manufacturers put. That's always the answer because they're going to put whatever the maximum capability. Now, I trust Rockwest more than I trust like Toray or Solvay or Mitsubishi or whoever. But
Uh, Our load case is also very high.
your load
There's
case is
actually,
very high.
yeah, yes. So it's
Yeah.
baked in there as well.
Oh, your load case has a high amount of conservative.
Yeah, yeah.
Yeah. I thought you meant that just your load case is super high.
No,
Okay.
no, conservative.
Yeah, it's just conservative. Okay. Yeah, okay. Yeah. Because you have to remember that like we can't simulate the filament wound at all
We're gonna
because the
test it.
orientation is a lie. Because the orientation is a lie. It's not plus or minus 45. It's like
oh,
plus minus 45-ish with like plus or minus 15, right? Like it's a lie. Um,
is there a way to use CLT to calculate things with it?
well, the ply is also non-consistent, like it's non-consistent because it
But how
just
would
matters on the quality of the winding machine they have. And I imagine it's good, but it's not an AFP machine, right? It's not going to be
mm,
perfect. It's just a normal winding machine. And so there's a little bit of, hand waviness to it.
mm.
Um, so that's
The
always
internet
the issue with winding.
calculations, how
Yes.
did they calculate it then?
Well, torsion test it, empirical test it. How did they
Okay.
calculate it? Like,
Hmm.
they're
Like
just
on their
saying what they
website.
input. They're just saying what they input into the machine. Now the machine, it's the winding machines are not
Mm,
accurate. That's what I'm saying,
I
right?
see.
It's
Okay.
the winding process is not perfect, right? And
Mm.
Rockwest doesn't make COPVs, right? So they probably aren't also operating with the best winding machines, right? They're
Hmm.
operating with good winding machines, but probably not the best, right?
Yeah.
And I see zero, 90 degrees in here, which I would always say are good for tubes, right? Because it can kind of help a little with compression, but you're just kind of screwed compression wise, anyways. Um, but no, this seems reasonable. How much did it weigh to the old ones we used to use before they removed them, which was very sad?
I don't have that number.
Oh my goodness. Okay.
I was,
Okay.
I was a tiny bit crunched for time making the slides, but
Well, okay.
well, oh yeah, and yeah, moving on.
Yeah.
So control
You have
arms.
nothing, Leo?
Oh yeah, Theo.
Sorry. Yeah, no, I don't have anything.
Okay, cool.
Cool. So control arms. This is the final thing I have for this section. Yeah. So for the design, we're going with 45553 roll wrap tubes, which are the same tubes as last year. And I can't quite remember the thickness. I was talking with Edward earlier, and I think it's 8 ply, but when I had it on the website, it said 10. So actually a little confliction there.
Yeah, it's
Um,
8 ply.
8 ply. Okay.
So
So
then
this
what's
might
on
be the
the
wrong tube that I had for the link.
it's well, note that it says 45553 Rev B. It's possible that Rockwest has changed the tube.
Oh. Mm,
So ye be warned. Remember, we're relying on a company to not change things, which is, not a thing they're going to do.
yeah, I know we do have some tubes already that Edward has stashed away, that we're gonna do testing with, but I don't know if we have any more.
Just make sure they haven't updated them since you bought them.
Yeah.
But like worst case, they updated them and add more ply. Just make sure that your inserts still fit.
Hmm. Yeah.
Um, but I imagine it's only going to be changing the OD and not the ID. So it only impacts arrow. So, who cares? Um, anyways, looks good. Yeah, just make sure you do your 70-75 testing. I
Yes,
don't
yes.
expect it to make any large difference, but
Yeah, we're still gonna expect to
technically,
use
from
the
an engineering
same.
standpoint, it should make a difference. So,
Yeah, I think we're like expecting a decrease in just the strength, but we're saving weight. Um, yeah, but like our control arms last year were pretty strong with Johnny's testing to get it a
yeah,
bit.
no, yeah, our rod testing has gone really well. Really,
Yeah,
really has. Used up a
yeah,
lot of
and
good
we'll
work.
be testing it again.
Cool. And pull rods,
For testing.
push rod front. Are we using pull rod or push rod in the rear?
Oh, can't remember. I feel like I should know that off the top of my head. Sorry.
Push in the rear. Thank you, Leo. Um, cool. Yeah, those seem pretty short, so I'm not too worried about buckling. Okay, cool.
Cool. Yeah, same chart and yeah. Oh, yeah, and here's for the manufacturing. So a lot of it's actually outlined in the testing doc, which I can send a link to after. And Wesley, have you review that? That'd be great. You, Leo, you too. Um,
Hmm.
yeah. So we just do the bonding procedure for the outsourced carbon fiber tubes, aluminum inserts. And I was talking to Johnny. I think he said last year it took him like about a day to like prep everything and get it all made. Um, but or that's not including the insert like machining time and cutting tubes. But um yeah, and here's a rough cost I did. So we each tube was like 72 inches. So we can get like 4, 5, or yeah, 4 tubes, and that should cover all all rods. Yeah, it's 24 rods, I think. So 328 total. Um, or do you or actually do you want to hear prices and stuff, or is that kind of more of a
I don't care about money. I just spend it.
okay, that's fair. Okay, I won't talk about that. Um,
It's good to know when we come to mold choices, right?
mhm.
Like selecting a mold and like why, like, oh, well, we're gonna make a foam mold and we're gonna do all this prep and here's the cost of the epoxy filler here, or here's the cost of the plaster filler and then the primer and then the, release agent. And then it's such a small part. So here's also the cost of the aluminum. Oh, look, it's really close in price and we get a better off part, right? Those type of things. That is where I care more about money. This is just you have to buy rods. Now, I'm sure Leo and, Ryan, they care about money. But like, you know, I just spend it. So, so yeah. Yeah. Okay. But yes, we'll go over the testing plan, 80 micrometers of a
Yeah.
glass and 60
Um,
feet of size Scotch Brite.
yeah, and some of those have to be fixed if it's 8 ply, so that's got to be updated for that the little
Oh,
table I have. That was kind of like a brief overview. Part of I grabbed that from the test plan of
Yeah. Usually we lightly abrade the inside of the control arms as well and clean. You're gonna always have to clean them. You like assume that Rockwest put a release agent on the inside and that like the release agent is still probably there.
Yeah. Yeah, I
And
think I
sometimes
remember
there's
Johnny
like
cleaning it with kind of like a screwdriver or a drill with the grinding paper on the inside to kind of clean it. Or
or just to abrade it. Yeah.
yeah, I braid it.
Yep. Cool.
Yeah, I think that's it for me. Um, what's the next slide? I think it's, oh, actually, no, yeah. So here's the overview of like the different oh, manufacturing.
Which this will change because we have some we need to look at some of the safety factors.
Yes. Yeah. But yeah, I just kind of
Mm,
like divided up into categories of like the different processes
we
kind of.
never saw the dash.
Oh, huh. That slide is I think I forgot to do that slide. But basically it's the same concept. I was thinking, or do we have a picture of the dash?
It's just mounting concerns for me
Hmm. Yeah,
and
shoot.
how that integrates with nose cone. That's it. That's all I care about.
Gotcha. I don't have a picture on me. Can we pull that up real quick actually so I get your feedback with the
Yeah,
mount?
there's a picture of the dash somewhere
There's an
here. Let me see.
interface.
Um,
Okay.
oh,
Oh, that's a
it's kind
terrible
of a
picture of
bad
it.
picture.
That is an awful picture.
If we're trying to open up 000, no.
Do you not have a picture on Discord or something?
I thought I did. I thought I had a slide. I must have forgotten. I exit this full screen.
I have 000 open. I'll send a picture in Discord and then Drew pull
Thank
it up.
you, Ryan.
Thank you.
But I was thinking like kind of, well, we've
We're
had
checking
feedback on the
outside.
upper firewall, but a similar like making like a mold, or male mold out of PLA and then fiberglass uh mold.
Why? Are we
It's kind
seeing
of
a
got a
lot of
complex geometry. Or you'll see the picture here in a little
are
bit.
we just seeing a lot of force in the dash?
Mm, not a lot of but more like the
Like
geometry.
like the reason we use prepreg for firewall is because it has to handle the heat, right? Like you have to. You can't use wet layup.
Hmm.
It has to handle the heat. But dash, then the next reason is like, okay, well, why do you use prepreg for seat pan? It's like, well, from a mass to strength, it's a stress failure ratio. Prepreg's better. So for seat pan, we can achieve a lower mass part. But for the dash, I don't know. Maybe the driver's putting 300 pounds to the e-stop. I don't know.
Oh, so you're saying you think we can get away with doing just like a wet layup or something and
Oh yeah,
just skip the fiberglass mold and just
yeah.
try to
Just
do
do it. Just
PLA?
do a lot of surface prep on it so that it looks pretty, and then Bob's your uncle, and then it will match the side pod and nose cone. Then it will
Hmm.
match the side pod
Hmm.
and nose cone.
Yeah, okay, yeah. I don't know why I didn't think of that, but yeah, I think you're right. We should just
Yeah.
do the PLA
Yeah,
and
you can do a wet layup
wet
and
layup.
make it a 3D print mold, or you can have some fun, make it a small super thin SMC part, or do whatever you want.
Ooh, SMC. That would be fun. Actually, I don't know if
Mhm.
it's like good for
It
thickness.
is. It's
It's
perfect.
I
It's
think it's
super
pretty
high
thin.
contour. And yeah, and you can do super thin. In fact, that's what most SMC parts in the world are.
Oh, so like actually do you recommend SMC for like a thin part like this?
Yeah.
Oh,
In
okay.
fact, you could probably buy like real SMC prepreg if you really want to. And then it's going to look better because the prepreg's always going to suffer with high contour. Actually, this is an interesting point. Could you do this SM two ply of the SMC prepreg, unless it's super thick, then you can maybe get away with one on the upper firewall? Mm.
Are you saying SMC for the upper firewall
Yeah,
or pre-preg SMC?
yeah. They well, because technically SMC is sheet molded,
Compound.
compound.
Yeah.
So it's short fibers cut, and then Mitsubishi makes it into a sheet, and then they sell it in a roll, like like everything in our world. They sell it in a roll. And so you can buy it in a roll rather than like making it yourself, like we did in the past, which is more of like a resin infusion. It's colloquially called forging, which is not completely correct, but it's pretty close. So
Um,
yeah, maybe you could do that.
we could discuss more about that later.
But honestly, I would just go with the like crappy 3D print mold. I don't think you need it to be that. I don't think you need to spend all the money to get a fiberglass mold out of it
Yeah, I that's
because it's
fair.
not that big and it's not a high strength part. The upper firewall is kind of big, so it kind of matters. But like if you have to do some like make the surface look pretty on the dash, if you're the person, it's going to maybe take you a day or two to do it on the dash. It's going to take you like 4 days to do it on the upper firewall. So yeah, yeah, CF nylon. Yeah, yeah, I agree with you, Utsav. I would recommend some type of sealant on it. Like maybe you can use the fiberglass gel coat on the 3D print. I don't know. Maybe, maybe to help seal it.
Just a quick question, just to make sure my memory is correct. For like our standard plate layups, we can just do those on like sheet metal, right?
We actually used glass.
Oh yeah, because glass I guess can get like a better shine, right?
And yeah, it's a perfect piece. It doesn't bend, and you really don't have to prep it a lot, and it's uber cheap when you buy shelving and or mirror from Home Depot, or in our case, we bought it from IKEA.
Okay, so we should stick to that just for our plate
I
layup.
I, I love the glass molds. They were phenomenal.
Cool.
They were
All right,
phenomenal.
perfect. I think that concludes it.
I
And
don't know if you had
yes,
an opinion, Leo, on the glass molds versus the metal plates,
Yeah, no,
but
they're really easy to use. My favorite part about them is that you don't have to prep them as much, like at all. Like
yeah, or at all.
like they're really easy to demold. They're really pretty parts. Like I think the glass is peak. The worst part about the glass is that's very easy to break, though. Like if mishandled or like if you don't store it correctly, like you're just someone will break it if you don't take care of them.
Yeah,
Yeah, we
do be
broke it last
careful.
year.
Yeah, do be careful, like, picking it up, and like the fact that, you have hot ceramic. If you put it on a cold table, it does the thing that ceramics do when you get hot cold, right? It will shatter. Um, but they're so cheap. They're
yeah,
so cheap and they're perfectly flat. So,
sweet. Okay, that's good here.
because the metal, I think we had one year where it bent, like we pulled so much vacuum on it that we bent the sheet metal.
Oh,
Yeah, you have to be careful.
Mhm.
It wasn't a lot, right? But like you pulled the part off and you're like, it doesn't sit flat. Right? Yeah. Okay, cool. Yeah. Neat.
yeah. Well, thank you
All
guys
right.
for the input.
Thank you so much, Ocean. All
Thank
right.
you.
Moving into aerostructures, we have Amaya, who is the aerostructures subsystem lead. Um, Take it away.
Okay. Hi everyone, my name is Amaya. I help with the aerostructure stuff. So today we're going to be talking about rear wing, front wing, side panels, nose cone, under tray, side pods, rear wing, air dams, and mounting structures. Um, so yeah. Okay. So the first thing we want to talk about is front wing. And there's actually two mounting schemes that we kind of wanted to go over today, the swan neck mounting scheme and like a tie rod mounting scheme. So with the tie rod, the front wing weighs about 10.27 pounds. Um, and yeah, that's an increase from last year's front wing by about 1 pound, but that's because we're adding internal structure to the front wing main because it's so huge to allow for better stiffness um, overall in the wing. So that accounts for 3 added ribs plus an aluminum rib, which will mount our tie rod too. So
How
yeah,
much does the aluminum rib weigh?
it weighs about 0.25 pounds, but that's without any like internal like pocketing. So just the brick of aluminum itself, it weighs 0.25 pounds.
Okay. How are you doing how are you we have a couple questions on this.
Yes, there's another slide like after this
Yeah,
that
let's
shows.
go through the slides. Let's go through your front loop slides. 2024 to 25. Actually, can I look at the weights real fast? Sorry.
Yeah.
For the 25, 25 to 26. Do you not have all of the previous years? Are we only looking at last year's, no offense, Clayton, but Piso Garbo?
No, I do not have the number for previous years.
Okay. But we have them, they exist.
Okay, I'll get those numbers for sure to get a better comparison.
Yeah.
Drew, could you go like one more slide forward? Okay, this is like how it's mounted to the
What
um
the?
aluminum rib. So there's two things that we kind of wanted to go with this. Sorry, the slides are a little bit out of order, I guess. But one thing that I think an idea was brought up that we could maybe weld on tabs to the aluminum rib itself. And that might be easier because the tie rod is at an angle. Or we can have like a clevis attached to a carbon fiber rib, which adds complexity. It is lighter. Um, but yeah, these are just some of the options we're weighing out. Right now, we're kind of going for the aluminum rib because you can just easily weld on tabs to maybe a plate, which then you'll weld onto the rib. And you can definitely pocket out material to make it lighter. But yeah,
Yeah, I just worried about welding accuracy.
okay.
The
And then
welded tabs are 0.13 heavier. Hmm. Yeah, but it's more robust. Hmm.
yeah, the honeycomb or not the honeycomb, the carbon fiber rib at the bottom, that one was like a 4 core 4, so 0, 45, 45, 0, has a factor of safety of 1.5. So I didn't account for like the 2 factor of safety. So definitely the aluminum.
0.1 for the clevises. Do you have the bolts in there as well?
No, I don't have the
The bolts
bolts.
are going to weigh nothing. But make sure you have the bolts, right? If we're looking at, welding versus bolts, have the weight of the
Okay.
bolts. Can
But yeah,
we do round head bolt nuts on critical fasteners?
I believe yes. I think that's what Clayton did last year.
Okay.
Oh no.
No button heads. That was what I was pretty sure of. No button heads. They might count this as a critical fastener.
Okay.
No button heads. Yep, it is. Thank you,
Yeah.
Ryan.
What was this? Yeah, I did not know that.
Yeah,
Sorry.
SES critical. Yeah, there you go. Yeah, look. See, I remember things. I swear. I swear. Yeah, just be careful. And don't forget the fact that when you weld aluminum, it technically changes the material properties.
Yes.
Um, yeah, I have a conversation about these carbon fiber ribs, but we'll get to that later.
Okay.
Uh, but okay. if welded aluminum, it's gonna be 50-52. Oh, okay, yeah, okay, no longer an issue. Okay, cool. Or not as big of an issue, but yeah, sure. Okay. Anyways, I assume back to the previous slide.
Yes.
Pull the lever, Kronk.
Okay, so this is like an overall assembly deformation sim. With max like speed pressure contour given from Aero, with side loading, bump load, and like the weight load.
Are we
So
saying that the car will never see above 65 miles an hour, including with front wind? Like, assuming you're going into the wind, we're not going to see above 65 miles an hour.
this was the max speed I used. Yeah, I should probably go higher.
Because Coda has like 30 to 40 mile per hour gust winds.
They do, and I believe, so correct me if I'm wrong, I do believe like air does take that into consideration because most sims are run at the average, which is around 30. But we asked them for 65 because that was our conservative like max loading.
Well, because we don't care. Yeah, but the car doesn't max speed see 30 miles an hour. They're running at 30
Hmm.
because that's where they're optimizing performance. That's a whole other different reason. So for
Hmm.
us as composites, we care about what's the max force, right? If we're doing a safety factor to 30 miles an hour, we're saying that we expect that, with our percentage, if the force goes above this amount at 30 miles an hour, then the wing should fail, right? So um, like we used to run max speed, and then we always had a rear wing mounting brake at Coda, and then we realized that Coda had like 30 to 40 mile an hour gust winds.
Hmm.
And so that was what was
And
breaking rear wings. So that's why, like, at the beginning of this year, I said, hey, either we stop driving at Coda or we start to include gust winds into our forces, because the reality is we're not going to stop driving at Coda. Uh, this car will. We are not driving at Coda. We are never going to have a VIP event at Coda. We're never going to have any event at Coda ever. Yeah, yeah. Yeah, it would be really sucky if the car broke at VIP, right? Like that would be really bad. Yeah. So we have to account for Coda, which sucks. But anyways, and then also like, okay, what's the max gust wind speed at the other location we drive at? I don't know. It's probably going to be less than Coda. Coda's ridiculous. But like there will be more than 20 mile per hour gusts. You live in the Hill Valley of Texas. So assume, and then is the car ever going to see more than 65 miles an hour? I don't know. That's an engine conversation. Um, but I don't know. It sucks because we go drive in a dome in Michigan where there's absolutely zero wind. But we have to account for, our ability to survive pre-comp and post-comp.
Mhm. For
So
that, would you recommend that we ask Air to run a sim at a larger speed, or
yes, Arrow should
is
run a sim at larger speeds, and they should maybe run a pure side-loaded speed. Or you could do this. You can say, okay, you should run let's assume 20 mile per hour gust wind for just every other day, right? So they should run an 85 mile per hour forward force. They should also run purely in Y, a 20 mile per hour force, and then you can combine that also with your 60 mile per hour force. So you should have a stacked pressure graph, or stacked force, or whatever have you. That is how the car looks when you purely side load it, and then you can combine the two together. Or you can create a vectored um, wind direction. But you should also test, like, if the car is just standing still, does a 20 mile per hour gust load fail it? Hopefully not, but or 40 mile per hour gust load or whatever, right? Core failure factor, safety of two on the outer end plates with and without tension cables. Maybe 200 newtons of side loading. Oh, okay. Maybe 200 newtons of side loading will survive.
But yeah,
And you
sorry.
so No,
I
continue.
estimated two. It was like the number was higher than two for the second and the second to last one and the last one, but I just estimated to two. I realized I should have put the exact number.
No, that's fine. Um, I'm assuming it's not going to be like something like 2.5, right?
No, it was like 2.03 and then 2.1.
Yeah, I would have maybe included 2.1 since you have the one before where the tens place exists. Because saying
Yeah.
like it's roughly equal to 2 and then having one above that has the 10 place in makes me assume that it's all like going to be like 2.0 and then below 2.05 or below 2.08, right?
Yeah.
Something like that. Okay. Yeah. Wow, look, cables do something. Did you account for the fact that the cables have to be in, like have a tension force in them that's already pulling?
Yes. So the way I did this is wait, what do you mean by already
Well,
account?
the cables aren't the cables don't sit at zero force, right? Because they're a spring, right?
Mhm.
So they're gonna sit with some amount of pulling force, right?
Okay.
And they're a non-linear spring as well. So as you tighten, right, it starts to drastically increase. They're not a perfect spring. That's why we use wounded cables. Anyways, so like when we do cables, we always are pulling some amount of tension. Usually, I don't know, it's somewhere between like 40 to 50 pounds worth of tension on the cable.
So that's
Because
like a
because otherwise it looks loose, right?
mhm. So that's like a load you add, like an initial addition.
Yeah, you'll have to add that initial load and you'll have an initial, right, deformation up. What are those linear springs with no pretension? Yeah, but it's impossible to have the cables with no pretension. Because then saying no pretension means that there will be slack within the system. Yeah,
Okay.
cables only work well when you pretension them first, right?
Gotcha. Yeah.
Like none of
So
the other cables in the car operate, or well, I guess when we used to have cables in the car, when we had them for shifting and when we had them for throttle, they don't sit at zero tension.
Well, I agree, but like, are you saying the pretension is gonna affect the deflection?
Yeah, well,
Like,
it's gonna pull it up, right?
oh yes, a little, but like, I guess when it's seeing loads, the assembly's gonna deflect, and
Yeah.
then the cable's gonna deflect with it. So
Yeah.
like, I guess is it a huge difference to just say that it's not like it's at zero,
Well,
right?
it matters who tightens the cable, right?
Yeah, I guess, but in terms of analysis, like I guess you'll have like
Well,
a
you assume worst case
reaction force
condition.
on the cable, right? It'll just give you like a spring force, and then that you
Yes.
can use that to pretension your cable after the
Yeah,
fact.
yeah, but like at zero miles an hour, there's going to be some force, right, that the cable's pulling at.
Yeah, but we're not really, I guess, looking at this at zero. I
Right,
mean,
right. So what you'll have is you'll have some force in the same vector as the cable, and then the linear spring on top of it, right? So there'll be initial like deformation, and then the linear spring starts at that condition, and then as it goes down, that force increases.
yes. Yeah, so uh are you or so how are you suggesting
you model this in.
Very with a lot of complexity. It's
okay,
it's not that because they're not a linear spring, right? Because
they're not.
the moment you get to the moment you get to zero tension, it all of a sudden has zero, spring force, right?
Mhm.
Yeah, so
So
I guess this like by doing it this way it tells you kind of like the threshold that you need to reach to ensure that your cables can act like a spring, right?
yeah. Well, like how
Like it,
much how much is it deforming at that location? It looks like like 65 to like 66 to 56 thou. So we'll say 60 thou versus in the other picture, it's deforming somewhere between like it's about like 75 thou. How much more weight is all the cables?
I haven't done the calculation for that.
Yeah, it's usually a lot. It's usually quite a bit. I wouldn't be concerned over an extra. I wouldn't be concerned over an extra 17 thou worth of deformation.
So you
I wouldn't have
wouldn't
cables.
recommend cables? No? Okay.
We had years of, Goose had cables because of a swan neck design failure. Then Panda had no cables. The Badger had no cables. Then Raccoon had cables due to a failure and due to a couple failures. I wouldn't I wouldn't have cables. We had years of no cables.
Got it.
Like have the ability to put cables on in case fuck something up,
Yes.
but otherwise don't bother.
Well, I think maybe the cables are because this is a heavier assembly than what we've seen in from I guess our years. Right? I think the cables are kind of a result of what the sagging we saw last year because of the
Yeah,
really
but
heavy.
that was because that main plane that they were relying on to be like the primary structure had
Mm,
huge gaps in the leading edge, so there was no like stress sharing. So it was basically operating as like two independent skins with no core. And it just wasn't a good it just wasn't a good manufacturing method mixed with like really hoping that it was going to be a good manufacturing method, and it just wasn't. And then there was no really good repair that was done on it because it would look bad, and the choice was to keep it looking good. And so then you had to add cables. Because the other answer is you had to put like multiple ply on the front, and then like you destroy what the arrow shape is and you make it look ugly. So, but that's how you keep the structure. So, yeah,
I
poor
mean, I
choices.
think cables are just giving you a backup option. We're not gonna primarily focus
Yeah,
on doing
yeah. That's
cables.
why I said like
okay.
I said like have cables like have like know where you would mount a cable, but I wouldn't bother simming it.
I think it's cool that there's
It's cool that
actually
it's simmed.
sim.
It's pretty
Yes, like we
cool.
have not simmed cables before.
No,
So like that's good.
yeah. But when you sim things, you should try to be accurate. And so what I'm saying is there is an
Yeah.
initial preload on the cable
Yeah, then it flex it upwards. Yeah, I
that
think I
flexes
understand now.
upwards. Yeah.
Yeah, that's
And
fair.
so that will change your arrow shape, and it will change, actually your like max deflection will, in that location, it will deflect down less to where it should be at 30 miles an hour.
Okay. Wait, so I have a question. Ryan, is this the max deflection thing that you're talking about with like stiffness kind of changing with its deformation? Like it's kind of hard to model.
Uh, I don't remember what I was talking about.
Okay.
He's a busy man.
No worries, no worries. Okay.
I'm EP.
Okay, so yeah, we'll definitely go with the intention of maybe not having cables, but we'll have the backup option available if you need to.
Yeah, this is cool to see as a backup option. It's also cool for us to see like what big amount of a difference does it make, right?
Yes.
And the answer is sub 20 thou.
I mean,
Yes.
with pretension and like it curving upwards, you could actually like
And actually,
really
yeah, you could actually
mitigate like all deflection, maybe.
yeah.
Like you could try to like design for it
It,
actually.
it would actually
Uh,
be kind of cool because at from 0 to 30 miles an hour, right? You're saying that like your wing is actually curved up. And then from
exactly.
30 miles and lower, then that's when your wing starts to curve down. There's actually like that's actually what they do in F1, right? Is they
Yeah,
have like
like
deformable arrow shapes and they actually map how it deforms at speeds. Yeah.
Yeah, that's kind of what I'm picturing here. But like you're kind of relying a lot on like your cables to do that for you, right? Like
You
um
got to do some math.
you got to but like yeah, I mean that could be pretty cool.
Yeah. I wonder if you just have an equation for that. You'd have to like Excel. You'd have to oh, that's how you do it. Your equation for your spring would be deformation times your spring constant plus the tension in the cable already existing. And that's how you would set the equation. That way it's always pulling at that constant force.
Wait, say that again. Sorry.
So your equation for the tension in the cable would
Hmm.
be your deflection times your spring constant, right? That's normal. That's assuming that the cable is a linear spring. Reality actually says no because wounded cables, because we use cables that are, wounded, there's multiple cables inside them. You actually get a friction factor inside that. That means that it's no longer linear. It's actually a progressive spring, which is really fucking cool. But besides that, so you'd have your deflection times your spring constant, then plus your tension. So whatever the force is from that.
Your pretension.
Yeah, that would be the simplest way to do it without having to like run an instron on a cable.
Gotcha, gotcha. I
Yeah.
also wanted to add that this year we're planning on doing like a sandwich panel spar through the secondary, the curved secondary, because like the airfoil is incredibly small, so we can make like a custom spar, which should give it more stiffness.
Yeah. Do you have a picture of that?
No, I don't have a picture.
Okay, can we go back to the okay, let's continue through these slides because I definitely want to review the structure.
Okay, sure.
All right, we've talked
Yeah,
about
I kind of
this.
went over fertility. And
Ooh,
okay,
what
so
the
this
fuck?
was this was we haven't put down the idea of swan neck completely yet. We are definitely leaning more towards the tie rods, but um the integration with the swan neck is a little bit easier as compared to the tie rod because you can make the rib part of the swan neck itself. But you can see that definitely it's heavier. It's about 0.44 pounds heavier. I haven't even accounted for the tension cables. So the added weight because of that, and also like the the large amounts of deflection you get as you like move outward of the middle section.
Yeah, and you're gonna have to have cables.
Yeah. And you know that like all these cables, like you're still seeing like large
It's
amounts of
still more deflection. Yeah.
yeah.
How thick are the swan necks? I assume they're aluminum.
Yes, so 60, 61. I made them 0.25 inches.
Yep, we that's ours were a little thicker on Goose, and hell, they deflected like they deflected like at the wingtip, right? Because you have the progression so far out. For y'all,
Mm.
it's going to be less of a deal factor because actually they're about in the same place. At the wingtips, we were seeing like 2 inches worth of deflection.
Oh, really?
Just in Y. Yeah, it was crazy, crazy.
It's really rough because you have to design some sort of compliance for it to work, for you to
Yep.
be able to assemble it. And it's like that compliance just like screws you so bad, especially on top of the regular deflection you're seeing. Um, but yeah, like, Swan X are so hard to pull off. Like the tolerance stack up analysis you have to do for this, and then like the precision of the manufacturing for this to get pulled off, like
It
required is
sucks.
really it sucks. It sucks a lot. But like I want this so bad.
I know you want this.
I
You know
want
my opinion. You know my opinion.
I think it's really hard to compare this to a tie rod using weight if it hasn't really been fully like optimized. Like there's like fat I guess you didn't have time to get to it, but ideally you would have tried to optimize that airfoil shape. I don't think you need that
Yes,
fat chunk
yes.
of metal in the inside
Well,
of the wing.
we have the same chunk of metal for the tie rod mounting in the
Yes.
Oh, tie rod also has a fat chunk of metal. Okay.
yeah.
Mm,
Yeah,
that's
it just
fair.
sucks.
Yeah.
It just sucks.
Yeah.
Um yeah, yeah. Welcome to my argument against Swan necks. It is an unoptimal shape. Oh well. It's cool. You could probably do it. It's like that's why like you see everyone does it out of like carbon, right? I mean, even we did it out of carbon, right? And it was lighter. But that's like the only way that's the only way to really do it because otherwise you're never gonna get that like Z directional moment stiffness out of the like aluminum. You're just never gonna do it without having to add cables or adding a secondary structure on top of it. Then there's the tolerance stack up, like everything we have said. It just sucks. It just sucks. Yeah, it's way easier to mesh this one next. That is true. Okay. Well, sucks to be a saw neck.
And this is just I apologize for the earlier mistaken uh the bolt, but this is just we're changing the size of the bolt from quarter 28 to 1032 screws. So this is just showing that I guess it can the loading that we're seeing on each clevis is below like the shear capacity of the bolts.
Please don't use potted inserts.
Don't use potted inserts.
Remember, we had a whole conversation about post add-in inserts and why they suck.
But we would do these during the layup themselves.
Okay, yep. Then they're no longer like technically potted
Okay.
inserts. Then they're like true actual inserts, right? Because what this picture is saying, right, is that you have. Feel free to disregard this question and you can correct me if I'm wrong. But it is. I'll read that later. Oh no, I kind of understand this a bit more now. What this is showing. Yeah, no, this is fine. Yeah. Okay, yeah. So like you could do the insert, I guess if you do the insert out of the like potting material, like the Allen key method that I told y'all
Mhm.
about, then it would be fine. But yeah, do them out of metal and delay it. But if it's aluminum, make sure you have something around it. Galvanic corrosion bad.
Galvanic. Okay. Wait, can we make these out of 3D prints?
Are they gonna melt in the oven?
No, if they're like the high temp, the carbon fiber nylon.
Mm, I would I would prefer because FDM sucks in compression.
Okay.
I would ask TIW to print it out of their kind of CF nylon that they use out of SLS.
Okay.
And then you can machine them. Then they're actually like solid nylon. And I would go with that actually over aluminum.
Okay. I think the TIW that is
Roger's gone, but
yeah.
the printer's still there. It's a Fuse One. It's the Fuse One. You can just
Okay.
make a ton of them. In fact, maybe to say this, I would add them to seat pan and to firewall because everyone overbolts the firewall. Any of your bolted connection, because people, especially the ones that other people touch outside of composites, every single bolted connection you should have some type of plastic insert. Boom. I would put that. I would put that in there. It'll be a little heavier, but the robustness of your parts will definitely increase.
Gotcha. Okay. Cool. Yes. Any more questions?
There's some stuff in the chat.
Yeah, I'm just reading. You'd have to like I-beam the swan neck, right? You'd have to I-beam that to add bending stiffness into the actual like neck itself. Um,
I just don't think it's thick enough to make it worth it. Like you're basically you'd have
no.
to pocket it.
Yeah, and you'd have to like it's only a quarter-inch sheet, so you'd have to buy like I don't know what, an inch sheet at a minimum so that you I-beam at least one side.
Yeah, just I think pocketing it, like the way it's like topology optimized is probably
And
better.
it's gonna weigh more.
Yeah.
And it's gonna weigh more. Um Could you go back to your bolt calcs? Charles brought up something I want to check because he is completely correct.
No, I have not taken into account the frictional shear capacity.
You should, like the whole reason we do bolt calcs really is because we calculate to what point friction, right? So what you do, actually, this is a super cool thing, right? Is you basically completely ignore the shear capacity of the bolt,
Okay.
and then you calculate it based off of friction. Now, that is what we do in automotive. They don't do that in aerospace. But in automotive, you can get away with like purely putting in like your friction force and saying that, okay, is my friction force now larger than my maximum amount of shear force that I can handle? And then you say, okay, well, then the bolt will never see shear. So that's how they do clevises in automotive. And that's how you can like have a super small bolt can handle like, Le Mans car levels of force, right?
Got it. Okay.
So yeah, you should.
Yes. Okay. I'll look into this.
Since friction can't be guaranteed at ultimate. Yep. TLDR do both. Thank you, Charles. You are completely correct. I would, yeah, I honestly, the other statement is you can also just sit here and say the bolt will not fail. The bolt's sheer yield capacity is more than what we're putting through. And
Got it.
you can just do it the aerospace way. And the aerospace way is, screw friction shear on bolt spec, and you just buy bolts that can handle the shear.
But realistically, we want to do both calculations.
Well, technically, what is lighter is having it be handled through friction.
Okay.
Like that's technically lighter. So, but you also don't have much. This isn't a suspension component.
Yeah.
This is a wing. So yeah, okay.
Okay. So for the front wing manufacturing, we want to make the front wing main out of 3D printed split mold using PA6 CF nylon, and then also the curved secondary. And the reasoning behind this is because we're already on a kind of on a tight manufacturing timeline. So the fact that we can 3D print, like we were able to 3D print an entire secondary mold over winter break.
But how
Using
long is it going to take you to prep this mold? Because you have a split in it.
So we added, like, we made sure there were like pegs, kind of like dovetails that connected them. They're not like shown in the picture, but hopefully by doing that, we can maybe make it easier to like seal the gap, which we plan on doing with like an epoxy coat or like a high temp gel coat. Um,
Yeah.
and like the second we get to the facility, then we can immediately start prepping these molds and start doing the
Are
layups.
these perfect sized? Like, is the surface exactly what it should be from Arrow?
Yes.
Hmm. I. Hmm.
Would you recommend offsetting it?
Okay, here's an interesting thought. Offset it, put a layer of epoxy or gel coat or whatever, and then machine it.
Okay.
So you machine the plastic to have a perfect finish,
Oh, okay.
and then you can then you're not having to dump the money like you would have to on aluminum. And since these are small, they're quite easy to do. Your only issue is going to be I don't think Jamie would allow you to machine plastic, which is a shame. But I don't think he'd allow you to CNC plastic. You can ask, but I don't think he will. Are you ever gonna use the front wing main? The stupid looking. Yeah, he won't allow. Yeah. Oztex machines plastic. They might do it for you. Um. Oh, Corin might. His machine's not super accurate. It's
I don't,
fine, but it's not super accurate.
we're trying not to rely on chlorine like
Yeah, he
too
also
soon right
costs
now.
money.
Too soon, yeah, especially too soon into the semester. I think because everyone's on break, there's not been like clear communication about like getting our
Yeah,
um
Oztex machines plastic. They'll do
okay.
it. They're in Hillsboro. They used to be in Austin, but they moved to Hillsboro, which made sense for them. Um, this front wing main. Um,
Oh, so like you surface prep it with like vapor smoothing it basically.
I don't agree that vapor smoothing is a good. I don't think vapor smoothing is good for our application. It's not good enough. $100. Yeah, but we're talking about free, Charles. Prior to your regular bold prep. Yeah, but we're gonna sand it anyways. Yeah, but who cares if you're gonna have to sand it anyways, right? Then you don't. Why vapor smooth it? Why spend all this money to vapor smooth it to then have to sand it still? Just sand it more. And you're still decreasing accuracy. It's not by a lot, but it's by a little. Like it's still there's still a number to it, right? I would honestly I would try the do a surface offset, machine to plastic, or do a surface offset, add a gel coat or an epoxy to it, then bring it to Oztex, have the machine it, and then do a test layup on it, see how it goes.
Okay.
I guess you'd have to do a gel coat because you can't do an epoxy coat because otherwise the pre-break's going to stick to it.
Did you not add like a some type of mold release between the epoxy and the
No. Okay. The chemistry is that it matters on what epoxy you're using. You can't, I don't think you can do, well, you can do free coat, but we're currently using a ceramic release here at Boeing. That's pretty good, but it does leave a film. Like, do note, it leaves a film. But it's a ceramic film, so technically it has less of like an energized surface, so it technically grabs air less. I actually did an experiment on that where you use like a wax that has a low energization coefficient. I don't remember the wording exactly, but it was basically like it chemically doesn't attach to air as well. It's pretty cool. Um, so you can decrease your boundary layer, which is pretty neat. Anyways,
Oh,
0, 0. Yeah, I would maybe add a 45. I don't know. Okay. Yeah. Just not like just remember what Clayton said in our first one, where he was like, he doesn't recommend 3D printing molds.
yeah. Okay, the reason we're doing this is mainly because of just like hoping to get some type of uh like gain before manufacturing season actually starts. Does that make sense?
Yeah, like doing a test layup to be like,
Yeah.
oh, we have this ply contour issue here. We have this problem here and blah blah blah
Yeah.
blah blah blah. Yeah, fine, fair enough. Yeah. What
Yeah.
is this still your true manufacturing plan though? Is to make it out of preprint or 3D print or what?
Yeah. So currently the plan is once we do this test layup on this one secondary, maybe we can also do it for the like the second secondary and then the main element because you skip the whole step of doing the extra like fiberglass layup on top of that when you can just put all of this in the oven with pre-preg.
Yeah. Yeah, it's just porosity. I guess if you gel coat over it, then it doesn't, then the porosity is no longer an issue.
Yeah.
Um, yeah, have you looked at like for this like tiny little, pedally freaking PA6CF 3D print, have you considered tooling board?
So we've considered a couple things. it mostly comes down to cost and like feasibility. That's like our biggest thing, and like we're gonna go into it more later, but one of the biggest things we're considering is using Pink Panther formula with what we've been using with just Gyro Shield, because at least in the Gyro Shield, like technical data sheet mentions that it's meant to mimic epoxy tooling board once it's applied to foam. Whereas actual tooling board is much more expensive. We do have a sponsorship lined up for a lot of tooling board, but it is low temp and it is probably not going to get here in time for when we need it. So it'd be great to have.
What's the temperature on it?
They said 200 and
Fahrenheit?
Fahrenheit.
Meh.
So it's like almost there, but not quite. They
Yeah.
did say that there's a failure. I forgot exactly the wording. The failure was like 400, but the TG was 200. It was 200, something like that. And because we have a lot of the Pink Panther formula, it's just kind of our best bet if we can go with that. We were also considering MDF. I went to Home Depot and checked it out. I do think it's a good idea. But if we already have the foam, um, I'm not sure it's a good idea to waste time trying something new when we can just perfect what we've been doing.
Yeah, but if you're perfecting a like fundamentally flawed process, right?
Hmm.
The only reason to do it would be for money.
Yeah,
So
that's a fair
just
point.
so just make sure that like, take the cost of this doing this mold out
Hmm.
of plastic, out of this 3D print, take the cost of the 3D print, multiply it by, I don't know, two, three, because you're going to have failures, right? Which you
Hmm.
had, right? And that's cost,
Hmm.
which you had. So,
Yeah, we're looking to test these as soon as possible. That way we can figure out what's best. Also going to speak with Intriclone soon about mold manufacturing timelines. So hopefully within the next couple of weeks or so, or maybe like 2 weeks from now, we'll have like a pretty solid plan of how manufacturing exactly will work. Um, but these are ideas so far.
yeah, we need to talk about the manufacturing stuff as well. Yeah, I don't know. Just I don't see like I saw costs throughout all of ocean stuff, but I see zero costs here. And this is where we need to look at money, right?
Hmm.
This is where money really makes a difference because these molds are huge, right?
Yeah.
Yeah, that's on me. I should have added some type of like quote or cost
Yeah.
dedicated to each mold.
Yeah. Because if Utsov decides that he wants to use his front wing main profile again next year, right? Because I'm gonna tell you this right now. No matter what you do, if you do not CNC it, you will never get a good surface finish quality, and Utsov needs to bump up his boundary layer by quite a lot.
Hmm.
Because you'll never have a good surface quality. I don't care what anyone else says, you will never have a good surface quality. End of story. Your surface quality won't be good and your accuracy won't be good. Like compared to machined aluminum, right? Which is what we have been using in the past. Like that's the honest to God truth. I
Hmm.
don't think Leo would disagree with me at all with that statement. Um, so so yeah, so just like take that into account, right? Like, are you going to be losing 15, 20, 25% of your performance because you're saving $50?
Hmm.
Or $400, and maybe Utsov, maybe and Graham, and Graham agree that this new front wing profile is what they want for future years, and they're going to agree that for the next 2 or 3 years they're going to use this front wing profile, and so you make it out of metal,
Hmm.
and then you can sit on this till the end of time.
I agree. I think it's just really hard to try to coordinate a long-term effort like that. I do agree.
Well, just Arrow
Yeah,
has to agree, right? Like that's the thing.
you, and then you have to like hope that the next leads also want to move forward with like this profile. I guess they're forced to have to move forward with this profile that may be very optimized for this current car. I do agree. Like, I think it's very hard to manage your profile tolerance without CNC. Like, it just the 3D printing. Like, there's no way for us to keep track of the profile tolerance and how much that's going to affect aero performance.
Yeah, because the
Um,
3D
so
print's never accurate.
yep. Um,
Mhm.
I was hoping to see a little bit more about our conversation from the first design review where we talked about um I guess the analysis going into uh deciding to go for a complex geometry versus keeping it simple. Um I think we talked about it the first design review where it's like how do you quantify like the gains from like an aero performance versus the cost of like increased manufacturing costs, design like the design
Complexity,
consideration,
yeah.
complexity, um, like analysis complexity, like all the additional costs on composites and costs like monetary costs versus like the marginal gains in aero.
And that's what they're going to want to. Oh, sorry.
Sorry. Yeah, like I'm sure this might have been covered a bit in the Aero CDR, but I'm really curious about from the composites point of view, is like how did we come to an understanding with Aero about like yeah we'll do everything you guys want and we took on these insane like or not insane but like complex geometries at what cost, right? Like what is the analysis gone into deciding yes like okaying that we want this design versus a very simple one. And
Mhm.
yeah, I guess having a baseline would have been good. I'm not sure if we're gonna get into that, but that's kind of what I'm hoping to have seen.
Yeah, and I'll tell you this right now. Like Panda, when we did phenomenal in design, and even in the video Multimatic released about, going to an FSC tournament in Michigan and they were talking about Aero, they talked about our car, right? They talked about what we did. No one else aerodynamically, just what we did. And their reason was is because Aero had a very good reason why they wanted to do things. And they had a great breakdown of how this complex thing worked and they were able to explain it. And then when they went and talked with Composites, Composites was able to say, we saw Arrow's gains, we knew it was going to be more complex, but we understood that for total car, this wasn't going to make a drastic change to our timeline. And we validated to ensure that it didn't. And then we used it within our simulations. And then we used it to help benefit the overall aerodynamic structure as well, right? Like we made a gain out of an arrow gain, right?
Mhm.
That's what the judges want to see. I see none of it here, right? This just looks like Arrow gave us a task. We build what we are told to do, right? This is very, kind of blatant, just kind of brain dead, right?
Mhm.
So that's what we wanted to see. We talked about this last time. We wanted to see what are the Arrow gains versus reasons that composites did things in the previous years that made the structure lighter, and how does that affect car performance overall on lap sim? Not if we're going to use lap sim and it's going to be a tool that we have, then we have to use it as a tool, right?
Mhm.
No matter how accurate or inaccurate it might be. And I don't see any of that, right? We talked about the end plates going full forwards through the main plane. Didn't see any, haven't seen. We just went through our comparison. We're in manufacturing. Haven't seen anything about that. Um, like Leo said, the why have this curvy? Obviously we decreased the amount of curve that we saw from last time, but why have still some of this curve? What performance gains do we see? Is it worth the complexity or weight change gains? Blah blah blah. We don't have any of that information here.
Well, I do want to
Mhm.
say that first off, in terms of complexity, there's only one secondary on the whole farming that is actually complex. Um, rest of this, the other secondary is a straight normal 6 inch, and yes, our main has changed, but that's been a design idea that's been proposed since the start of summer. And Second of all, is the reason we went for the curve is because we did not want a mid end plate again, like last year's, because that had a lot of flexing in our throwing. And yes, of course, the main was a primary cause for it. But attaching, first off, our wings were never cut properly. And second of all, was attaching them together was really bad. And that's literally why in the front and the main we had a bunch of compression on the front wing, but towards the rear, since the wings were cut short, you just had a bunch of tension, and that's what created the weird sagging and all those weird stupid geometry errors that happened last year. And we are just trying to eliminate error points that can occur because I mean we're human at the end of the day, right? And we can make
Yes. Yeah.
mistakes. And the
Honestly.
whole point of going for a whole secondary that's combined together is mainly because of the fact that we've had a lot of errors in the past and we know we're on a time crunch. It's better to just do things in one simple body rather than add a bunch of end plates in the middle.
Yeah. I don't think any of us are disagreeing with that. I think we're saying is why not make this one continuous rather than curved, and just ditch the middle end plate altogether, right? Does it need to be curved? Like
Yeah, we
why?
have
What's the
bounding
performance
boxes.
game? What's the okay? Then don't have the raised up higher bit because you have a bounding box. There's a constraint, right?
I
So
mean, then you
like
lose performance.
right, but is that performance gain worth the complexity, right?
Yeah, I
Look at
mean,
look at
just
our look
to
at our front wing. I guarantee you the structure would be better if you had the end plates that went all the way to the front of the wing and went through the spars that go through the
yes,
center. You would have to have
yeah,
no more spars in your secondary and tertiary element, period. So but we didn't see any changes to that. And that was actually a requested thing to be seen in this presentation. That was requested at the last one. We don't see it.
wait, sorry. What about the spar? What do you mean by the spar not going all the way?
It
Well,
Oh,
needs to
through
no,
the
further
end
sheath
plate, you
kebab.
say?
yeah, through the
Okay,
through the inboard end plates. If your inboard end plates go through the front main, then all of a sudden now you have this structure that goes all the way back, and now you don't need as much structure on your secondary and tertiary element because now what you have is a inboard end plates are basically floating, right? And so you're basically relying on your secondary and tertiary element to provide most, if not near all of the structure, because it's not going to get a lot of support from the wingtip, because the wingtip's not a super strong area, right? It has a very low cross-sectional area. It's a very thin ply. It's never going to be the most optimal. So you rely on spars to make sure that that element is that inboard end plate is capable. But that was something that was requested actually by John in our last, you know, get together.
yeah, fair
So
point. I mean, I can just kind of remember things on the top of my head. We tested it. I mean, just the data's not here, but um, it was an overall 6 point loss, I believe.
so
Because
what's that to so what but what's that to lap time? What's that to when we have
about
that
lap time,
structure
I mean,
change? Yeah.
you lose about if you add. Let me try to remember this correctly. Um, I mean, I can run the numbers again, but
Yeah, right. Like, but the structure is going to
it
be
it, it was a
lighter.
lap time, big lap time loss because like the current lap time we have or laps in we have, it's pretty, I would say, sensitive for error compared to weight. And even if we add like a pound compared to like a few points of downforce, we still gain a decent chunk of time. So
Yeah, but we also have to remember that like we're pretty accurate on weight. We are very much not accurate on CFD to reality.
I mean, yes and no. I mean, you have no way to say it's not. So like it's like
Well, I have every other piece of data from every other car company, every aerospace company, that says like you do everyone does a wind tunnel test. There wouldn't be wind tunnels in F1 if CFD was accurate.
sure, but again, we can't quantify on our car. That's the whole
Yeah,
point of validation.
we can't currently qualify it. But that means that, we can't, for that part, you have to take some things with a grain of salt. If the direction of the team is trust, then trust we will. If the direction is, well, then we have to be realistic. But that's where realism, comes into play as engineers, right? Like we have to be realistic, right?
Yeah.
This goes back to the ergo, right? Ergo doesn't, a driver is never going to put in a perfect point force, right? They're going to do weird things with the steering wheel. So realism is something we have to take for account for in composites because the material isn't as forgiving due to its non-isotropic nature and the fact you lay it up as sheets. Anyways,
And
okay.
sorry, really quickly, later down the line, we're going to talk about like some of the ways of like validating our aero composites like together. So
Hmm.
yeah, that's definitely something we're working on to make sure that there's some way to understand whether or not like our CFD, like how accurate our CFD is to reality. So yeah.
Yeah. Not running future work. Those bolts got a lot of thread on them.
Yeah. Sorry.
All good.
Yeah, I guess
What?
I kind of sorry. I just want to reiterate, like, I think the biggest takeaway is, um, like how do you come to the decision to sacrifice your geometry and your quality of your part versus like a like right like what CFD results whether you're getting and like how much of a gain CF like can you see in CFD versus like a loss that you take from in terms of not just like labor and manufacturing, but like the quality of your parts and like the quality of your tooling, right? Because right now, like
Yeah.
the idea is we have these really scuffed 3D printed, glued together molds, and like post process, we do the plug, like all that, right? How much of a loss can we take from that like manufacturing process versus your slight like extra curves you're adding to this front wing, right? Versus having like nice aluminum tooling to make everything like simple geometry that's very reliable and gives you a really good geometry accurate to your CAD and to your CFD versus like sacrificing your design. Um,
Yeah. Or
so
even saying like, yeah, we can do the crazy curved, but to make sure that we keep the same boundary layer surface conditions, it needs to be out of either a metal or a tooling board so that we can maintain surface quality. Because we're composites and our direction from the team that was talked about at the beginning of the year was, don't make shitty parts again, make
yeah.
things not look like shit. So, if we start playing around with shitty molds because we're trying to be fast, then we're going to make shitty parts. And exactly like you said, are you now losing it?
Yeah, there we can move on. I think they get it, but I think that's a really important point to hit on moving
Yeah.
forward.
Yeah, thank you guys. Yeah, that's definitely something to consider since it's still relatively, we can still make changes to our molds, and change the way we approach like this manufacturing season. So thank you so much.
Yeah, I
Thank you
mean it's
guys.
a little late because I think this ideally would be a design decision, right?
Yeah.
This would be something you have to do early on with Aero for deciding your Aero package design.
This is why we wanted to have this much earlier.
But like yeah, I mean you can do whatever the best you can now with the tooling and like try to put a ton of time into it. And I hope that everything turns out very accurate to your design. But like, yeah, this is kind of a cost, like a right cost benefit analysis you do early on, in the
Hmm.
design process.
Yeah.
Yeah,
Okay.
we'll do our best to kind of amend that. Thank you guys. So moving towards the rear wing subassembly, this one is not as far in the development without the FEA as the front wing was. Our main items to focus on here are mounting structural analysis and started to focus on aero loads as well. A lot more focus was on the mounting structural analysis on this part, on this assembly.
Yeah.
So The ply layout internals, end plate, very similar to previous years, four core. The main, this time also a four core, uh, or not also, this time a four core 045 45 0. Um,
Main ply,
and
four ply, secondary is two ply. Just do zeros and zeros. You're never gonna cut them in 90. It doesn't matter.
okay.
Um, but it's basically the same thing.
Mhm.
Cornering to shear.
So when speaking with the Maya and Utsav and Grant, understanding of like why, like where these forces really happen on the car, especially these wing elements, one of the big things during cornering is shear. And from my best understanding, the best way to mitigate that within the parts is to add 45s in the layup. So changing it to four core, there's some results later on that I may will go into more deeply explaining that, but it's like in my opinion that would best help the load case be distributed through the entire assembly. And I'd like to hear y'all's thoughts on that. What you think about moving from the original two core or the two ply design we manufacturing process we've been using for years
For the
towards a four
main,
ply for the main.
the main's just so big. We were looking at moving it up anyways.
Hmm.
You just
Okay.
have to make sure it maintains symmetry because it's pre-preg. You'll get some
Can
warpage if you don't.
people hear me? Is this
Yeah,
like,
Yeah,
okay,
I can hear
sweet.
you.
Uh, I think you should really go back to like your free body diagram for like which direction you're putting shear in. Because
Hmm.
that's like really important. If you say like, oh, I corner and then I get shear, it's like, yes, maybe, but it's very hard, I think, for the audience to agree with you if you don't tell us which direction of shear,
yeah.
because in a
Hmm.
straight line, you also have shear.
Yeah, I have no real clue what you're talking about. Just kind of moving on. But
I should just
we
say.
already knew that we needed to, and you're completely right, Charles. Like if you're gonna start talking, if you're gonna start like diving into like big fundamental words, then you really need to on large, complex 3D geometry, we really need to know like, well, what is your critical direction of shear? Is it interlaminar shear? Is it shear across the end plates? Is it, like in the end caps? We're not going to
Hmm.
know. Because if it's shear
Yeah.
across the end plate and the end caps, then your bolts and especially your inserts become super important. If it's shearing between, so like if that would be XZ shear, right? But if it's XY shear, where it's shearing between, which we've seen before from straight line, speed, like what Charles was saying, where like the wings deform in, and so it pulls and shears against the end caps, then we can see that as well.
Hmm.
So the four ply yeah, I don't think anyone here is gonna I don't think any of your alumni are gonna sit here and go, oh no, the four ply. Um, because we all kind of agree we all kind of agreed that it was we've seen some failures on it being two. It is a huge main element. Um, the simulations say that, with arrow loads, even in cornering, side loads, two ply works. And it maintains a good safety factor. What we've kind of realized is, the answer is that, well, arrow is not always the most accurate. So, you
Hmm.
have to be kind of cautious, and it's this huge part, and it's super critical to arrows performance in this area. So it being four ply, yeah, it's a lot of weight,
Hmm.
but it's not the
Yeah.
worst.
I want to
Gotcha.
follow up by like saying I think like what Wesley's getting at is that it's a fine move to try and increase the stiffness of your main element, but I would question if going to four ply is the best way to do that. If you
We
just
can't go
look at
with three.
Well, if you just look at the structure, it's going to generally be membrane dominated. So like
Yeah.
the skin is going to move kind of as a membrane. And so the Canon solution to solve that in terms of deflection is to lower your unsupported span, not to make your membrane thicker, because the
Hmm.
returns are much slower to catch up from making your membrane thicker. And so I would consider like what's the weight trade or what's the complexity trade for, hey, why don't we put like a mid rib in
It's
this
it's com
wing?
it's complex. It's with how this wing is made, it's a little too complex. But I completely agree, Charles. Like otherwise, yeah, that's the way you go. You add
Okay,
more internal support, but yeah, it's complex. But that's
I,
completely fair.
I really think like even if it's just 3 or 4 hours, like concepting things out on a whiteboard, you guys are like smart engineers, right? Like try and present
It,
a trade space that like uses the canon solution because it's the canon solution for a reason, right?
you you you
Like,
Hmm.
you can't because of how the wings are made. The wings are made as one big monolithic shell, and so there's no really good way to add adhesive to the center because otherwise then it's just sliding. Sure, you decrease your moment, but like it's gonna do less, right? Like you're gonna prevent more Z direction move, like you will prevent more Z direction stiffness. You will have to add another spar into the system so that the rib doesn't rotate. Um, but it would be really hard to bond
the top of my
the inner
head,
rib.
I can say that I can think of a way to solve that, right? Like if I 3D print something that has an internal channel and then I use like an extension on an epoxy gun, I can inject adhesive into one
Yeah,
nozzle and have
yeah,
it
it's just a
squirt out the
really,
sides.
it's just gonna be a really long extension. It's just,
Yeah.
No,
it's
I
not, it's
agree.
non-optimal. It's just a non-optimal thing. And then it's really also hard to say like, how much epoxy are you adding and what's the weight on that? Um,
I agree.
Well,
Yeah, it's
that's controllable, right? Like you can say I've pressed this much, I know the internal volume of my extension. I agree with you that it's complicated,
well, and
right?
then bond
But like,
coherency, and do you have voids in your bond line? How do you account for that? I don't disagree. I completely agree. Like, we're composites. Everything we kind of do in Aero is one big membrane. It really kind of sucks. Um, but yeah, like it's definitely like I was gonna bring this up with front wing, and I guess we'll bring it up now, right? Like your center rib, you make it out of plywood. You make it something that is ridiculously light. All it's doing is it's providing some, support to the
hmm
system. You can look at it, it is going to be more complicated to make. And your
yeah.
accuracy of making the internal skeleton, because of how much we care about the leading edge quality in our metal molds and how important it is to Aero, that the leading edge isn't hot garbage. um it really does make it does really make it more difficult. but
hmm
it's but that's completely not saying that Charles isn't wrong and that you shouldn't look at it. It is just
hmm
for Charles's sake. There is some, like, we have I have thought about it. We have thought about it in previous years. I don't know if this group has thought about it, but it is more complex. um
hmm
but it is a massive rear main, as I'm sure you know, Charles, and it is the increasing the ply is, it's not going to hurt anything.
I
Okay,
understand the
also
general
just so
scope of the problem. It just like please have something to where even if you choose not to go with it and you choose to just beef up the ply count, like
Why?
have something that at design presentation you can say, we considered going for a more theoretically optimal solution. Here's why it wouldn't work due to the
hmm
manufacturing constraints. That's the ask,
Yeah.
right? Like it's not
Yeah.
go with my solution, bar none. But
hmm
okay, also
yeah,
just to mention or put it out there that I don't know why the photo doesn't have this, but from all the discussions I've had with composites, we are planning on doing a rib. We are planning on doing ribs on all the secondaries and the main too. It's just the photo doesn't have it, which is weird. But
In the
on
middle
top
of
of
the
that, last
wings?
year at comp, we got totally flamed for how flexy our wing was,
Who
especially in the
cares?
rear wing. So it's
Sorry. We have no, like, that was a judge being stupid. I am not going to, there are stupid judges. We had the ergo judge that like couldn't fit in the car and complained why he couldn't fit in the car, right? but it's like, okay, but you're, I am a large person, but there's no reason why you should design a car that doesn't fit around your drivers. Like
I
it's
mean,
it's not my
this is
400-pound
completely
life
like,
and my FSAE car, right?
I mean, but it's
But like
completely
we have
dependent,
no
right?
we
Like at
have
the same time,
no
I don't know for sure that my judge would be okay with it. Like we
Well,
got a
did
design
you go?
for.
Didn't you go and you tell them the exact same thing we told them at Panda when they went and they pulled on our wings and they said they're flexy, and we said, well, we have data that says this is how we make the lightest structure possible, and we have no data that says this amount of deflection is the minimum amount of deflection from an aerodynamic standpoint. There's no physical real world data. So we design to our minimum constraints that we have present for us. And that minimum constraint is the aerodynamic rule that says a certain amount of force with a certain amount of deflection. So that's what we designed to. That's why we
So
created the two ply. And in
so
fact,
what I want to
one
ask.
ply worked, and we went to two for robustness and porosity.
So how do you propose we get the data for proving that whatever deflection we're getting, and then on top of that, how do we prove it that it's good or bad or wherever?
You need a wind tunnel. You,
I
you,
think
you
a
either
more like
That's super high level compared to where y'all currently are, both aerodynamically and from a composite standpoint.
So that brings me to the next point. Do you think it's like, I guess I can't think of the word, but I guess, do you think it's possible for us to do these testings and get this data currently given our state?
Not with your current timeline to this coming year.
I think that the best
Not
we
unless
can
y'all
do
manage to
is
like sneak in like Peterbilt owns a wind tunnel here in North Carolina. Not unless you snuck your car in here. I don't
Mhm.
like I don't know. Um, because it's hard to do it as a scale model. It's hard to do it as just independent cascades within a wind tunnel.
Mhm.
Like it's better, but like adding all of these ribs, like it's I will give this to Charles. With how we make our wings, the tailing edge is not connected. We bond it together post. So for the big rear main, it's possible that you could add it in as one big skeleton. Now for the secondaries, I wish you luck. Because those really do not want to open up like at all. So it's going to be really hard to add in the ribs. And on top of that, every single area where you have an internal skeleton rib, it needs to look like what it does on the front wing, where you have at least two rods within the structure. Because otherwise, how are you locking out rotation around the single spar? Right? How are you locking out that rotation? And the answer is, well, you aren't.
Mhm.
Right? In fact, we had some of those issues with Badger, where we removed the secondary spar in the front wing, and we saw that it rotated a little more. There was a little bit more play in it. Because we removed the kind of anti-rotating, we allowed freedom in the Y direction for our wing element internal spars and the internal
Mhm.
end plates that were used to spread the force. So that wasn't, most ideal. Like you're making it to where all of your wings independently have to handle the torsion um, between the end plates for the front wing. For this, there's a lot more bars, less of a problem. Can still be a problem, but it's usually less. Um, yeah, there's a lot of bars in this wing. I'm not sure if like yeah, the eternal ribs help. It is technically from a theoretical standpoint lowest mass, but you're really adding manufacturing complexity
Mhm.
and you don't have any way to validate that increasing the mass by a little compared to like increasing ply count for an increase in aero stiffness actually is going to make any of a difference. Because we could be seeing that at higher speeds that the that the wings are actually seeing a lower amount of drag. And so therefore we're actually seeing better car performance because the wings are deflecting, right? Like we don't know because we don't have any
Mhm.
number.
Right. I agree with both of you. I think it's important to like understand like if it would be beneficial or not. I did also speak with Clayton and Amaya about this a bit on ideas of how to like prove against design judges. A consideration that I've been thinking is that um, when, say, for example, actually, I think I've spoken with you as well, Wesley, about this. Like when they
Oh,
press, when they,
sorry,
uh,
hold up.
mhm.
All right, try again.
Hello, hello, test,
Yeah.
test.
Yeah. Sorry,
Yeah,
my headset died.
you're good. You mentioned how like a finger pressing might be a quarter of an inch, a quarter square inch, whereas that would create a large PSI compared to the aero load, which would, even though it's larger force, it does not create a larger pressure because of this distribution. And
Yeah.
I think that that might be the best bet having these simulation results proving against what the judges would say, because you're right, we're not going to sneak into Peterbilt and, run our entire car in a wind tunnel.
Yeah.
But I
But it's
do want
good.
to,
But it's good to acknowledge. It's good to acknowledge to the judge, like, yes, we understand the wing deforms.
yeah,
Like, right?
but it's okay.
It would be silly to say it would be silly to go to your suspension system and say um, tires do not deform, right?
Hmm.
Like we understand the wings deform, and that's okay because with our current like one, if you put like here's a penny. Let me put this penny on your finger. This is the amount of psi that the arrow is actually putting on at 30 miles an hour, right? So yeah, it's the issue is this is a very important thing because this is gonna be a question we're gonna get. We're the only team that runs this light of an aero package. We're the lightest aero package at every single comp, right?
Hmm.
Even when we do a shit job, we're still the lightest aero package at every single comp. And
Hmm.
there's fundamental reasons why we make those decisions. And yeah, y'all need to understand them as much as y'all need to convince the judges too.
Yeah,
Definitely. Yeah.
I agree. Let's say we could probably move on. I do want to add one thing. Like we all know that empirically we're not the greatest. It's very difficult to get empirical data, but we do have a pretty well developed aerodynamics team, and I think we can trust our CFD enough to try to see how much a deflected shape can affect uh like our aero performance, right? So I think that's my suggestion. If we do want to have a deflection quantification, a way to like some sort of guideline, something to show judges like our own interpretation of like our like deflection instead of just looking at the rules. It would be trying to create some sort of like just data data points of deflection versus um like loss in air performance or gains in air performance, right? Like
Hmm.
Yeah.
stiffness. So like that's the way you would go about it. So you would work with right with our FEA, you would take the deflected shapes, throw it into your 13 meters per second full car model and see what kind of losses you're looking at, what kind of gains you're looking at for a deflected ideal like infinitely stiff uh like geometry you've been working with. I think that's, I mean, given that all of our aero decisions currently are just made off of CFD, right? I think that's, but we can still rely on our FEA to try to influence our deflection results as well. So,
I agree.
of,
I,
of
I
course,
completely agree.
of course, empirical data is the most valuable, and that would be so valuable for this team long term in terms of making decisions. For now, just get some theoretical, like some like get like a graph of deflection, stiffness versus like your CDCL, and you're probably it's not going to be linear, right? It probably isn't going to be linear, and you can probably weigh that versus you have like a three-dimensional graph versus weight and
Yeah.
just try to find some optimized like that's that I think that's how you would determine like your deflection um like target, right? Versus right now like it's just like following rules. Um
Hmm.
so that's how you would develop that.
Yeah, and
Um,
I think we had that discussion earlier with creating
we
a
did.
3D graph.
Yes.
I think honestly, what you could also do is like create a composite wing that I don't know is like 12 or 16 ply, something ridiculous, and throw that in the wind tunnel, and then
Hmm.
compare that to our current CFD settings that we have in also a wind tunnel. And then that will give you like an idea on like what accuracy our CFD is to pseudo reality, right?
Hmm.
Wind tunnels, as close as you're going to get without like having like 5 billion pitot tubes on a car,
Hmm.
right? Without
Yeah.
making it look like spaghetti. There,
Hmm.
that's as going to be as close as you're going to get, and that will also help with gaining some confidence in the results that CFD is currently giving, right? As
Hmm.
well.
Yeah.
And then you can also look at, then you can start to, then that starts to really, open up what you can do with surface quality. Because then that also gives us a value to the importance of surface quality.
Yeah. I get you.
I do want to add that the at the very end of this presentation, we talk about the error validation where we bring up all these points. So I'm really glad you brought them up. Like you guys brought them up right now because we're definitely going to hit on them before like the end of this presentation.
Hmm.
Yippee.
Yeah.
All right,
All right.
continuing on.
So, Amaya?
Okay, so with the entire conversation that we just had, it's very hard to actually quantify whether or not this needs to take place, as in that we need to add the internal structure because there is a delta of like 0.11 inches of deflection with zero internal structure in the front in the main element.
What
With
speed is that at the max? Is that at that 65
yes,
mile an hour?
max speed.
Okay. So
Yes,
when we do aero stiffness analysis, right, which is like what value aero puts to deflection, right?
yeah,
You need to run that at the 13 meter per second speed
okay,
because they're
Why?
not looking at what is aero performance at 65 miles an hour. They're looking at what is it at 13 meters a second, which is like 30 miles an hour or something like that. So like
Hmm.
so this is the max speeds, and I know we had this discussion before. The max speeds are good for the max speeds are good for our like failure analysis, right? That's where we're looking at like, is this thing going to break? And then the 13 meters per second, the 30 mile per hour speed is good for being like, oh, by the way, Arrow, if we add an internal structure, it's only 0.01 inches worth of saved deflection, but it costs a whole, pound across the car or 2 pounds
yeah.
across the car. Also, love that the dates and times on these are visible.
Hey, if you look at
Just
all of
Whoa.
this, I'm pretty sure they're all because I opened them all like they're all open today, so they're gonna be like in like one after the other in like 30-minute intervals.
hmm.
I'm sure you just opened them and took screenshots. Like I'm sure these
Yeah,
simulations like
Yeah,
yeah.
yeah,
ran a
These
long.
Yeah, of
simulations were
course.
done 3 months ago. Yeah.
Yeah, exactly.
Absolutely.
Yeah. Okay. There's only two ribs, one spar. Yeah, we had the discussion about the difference between with internal structures. So when you mean two ribs, one spar, is you're adding two ribs into the internal. It's not just the
yes,
end
yes.
caps.
Yeah, and
Okay.
they're 0.1 pound carbon ribs.
I would almost from a weight saving perspective, because there's not much force going into those ribs, right?
Yeah.
Look at wood. It's
Okay.
what we did for Goose, man. It was so good. There was some accuracy issues, but because we were putting them in curved areas on a wet layup that wasn't really accurate from the start, anyways. Um, but man, it was light. But I would also recommend going up to two spars because you have no rotational control, right?
Hmm.
Like, be careful because I don't know in your simulation, do you have it to where the ribs are fixed in all directions against the spar?
Yeah, I do. I do have that.
Right. So that's not entirely true, right?
Yeah, yeah.
Unless you do a lot of bonding, then you also need to include what's that bond failure, right?
Mhm.
on such a very small cross-sectional bond area, right?
Yeah,
So you'll likely see bond failure, and then you know, and then it doesn't matter. It's just going to rotate, and you keep the shape, which is super important. You'll have some resistance from shape control, but like it's not going to be this good.
got it. So you
So
recommend having two spars if you're gonna run a spar through your
yeah, if
block?
you're gonna have middle ribs, run two spars.
Okay,
But
got
you're just like guaranteeing that you're mechanically locking out
Hmm.
rotation. Like you can do the like bond math, but and like you can like load point it to see like how much like force is going over and see if you're like failing, you would be failing a bond. But knowing that it's probably super thin carbon within this, you're not going to have a lot of bond area from the start.
got it. Okay,
Yeah, that
Yeah.
makes sense. Definitely something we're going to consider.
Yeah. So I would run a sim of this with all of the ribs not fixed in rotation around the spar and then see how worse it is.
Mhm.
got it. Okay, wait. Thank you.
Alrighty. So moving on to the structure, this is where we did a good amount of analysis. A couple members of the team, myself included, we were talking about degrees of freedom, constraining it. Looking at last year's mounting structure, even on Badger right now, sorry, on Raccoon right now, you can kind of go and wobble the wing a bit. And
that's
as
from
you've
a
mentioned,
that's from a
that's from a
different issue.
manufacturing issue for sure. But from what you've mentioned, Wesley, about like crosswinds, something we took into consideration was the degrees of freedom. So 2 bars would bring us down to 4, whereas 4 bars would theoretically bring us down to 0, but there would be I'm not sure it's the right term, but like a structural brace within the wing, whereas 6 bars would allow 3 on each side, which make a plane. So now in this case, with no wings attached to each end plate, each end plate um, is still not able to move.
That's just
Um,
not true.
Yeah, I was
but
about to
not
say that's very much not
Like
how this works. Have y'all
there's
ran
no
the simulation I told y'all about?
Clayton
you
mentioned that
don't
he ran it, but I don't have it with me here.
you don't
Go
need
ahead, Charles.
simulations. This is like fundamentals of kinematics and mobility analysis. Like you basically say each one of these bars is constraining 1 degree of freedom because they're not collinear with each other, or they're not like perfectly parallel for an instant with each other. And then it acts as a single constraint because it is a distance constraint between 2 points. One is a rigid body. You assume the other is rigid within itself. Like I've gone over this with Amaya and Clayton. It is a mobility analysis. 6 bars is the amount you need. Please do not present to anyone that 4 bars constrains a rigid body. Like that
Yeah,
is
he
not.
he
Okay.
he it's true. Because the reality is, right, is that you're saying like, well, 4 bars constrain a rigid a body. And he's right. It's not true. There's maybe a way you could get away with five. Okay, it becomes weird. Is what kind of the statement is. I've seen cars that have done less than 6, but it's weird. It's less than 6 with all sphericals, right? But
Hmm.
it gets really weird and really funky really fast. There are still ways that you can make a 6 bar not constrain all 0 degrees of freedom or all 6 degrees of freedom. Like there are still ways that you can fuck up a 6 bar.
Hmm.
Which I'm sure Charles will completely agree with me. There are ways you can fuck it up. That's why it's so important that nothing is parallel in any sense of the word, right?
Hmm.
To
It's
anything
important
else.
that each 3 points create a plane that in itself would be constrained and not parallel with any other feature.
Well, the it making a plane is it making like 3 points are always going to make a plane, right? Like,
Hmm.
it doesn't matter where. But if I put three of these bars right next to each other, and then if I took two of these bars next to each other and they were perfectly parallel to each other, and then I put one bar out in the middle of space, it might not constrain your degrees of freedom.
Hmm.
Um, because there is some like it's hard for me to explain because I
What
am
Wesley's
not perfectly a
getting,
kinematics person.
what Wesley's getting at is that there is going to be some imperfectness in the lengths of your bars, and your attempt should be to minimize the total change in the rigid body position for a unit change in that bar length. And so when you cluster, like he was saying, two of your bars parallel and very close together, and one very far apart, changing the length of one of those short bars causes a massive rigid body rotation about the axis defined between the other two bars. This is like, again, fundamentals of uh, like robot design or kinematics. Like the specific action I think you guys should do that I've already talked with, I think Clayton and Maya about this, is either in your trust solver, go change a link length and see how that affects your loads. Generally, if you have like a poorly conditioned setup, you're going to see large changes in loads for small changes in lengths. That's one way to do it. The other way to do it, if you're feeling like a little bit more lazy, is go into SolidWorks in an assembly and create distance mates between the points that you care about. And then
Hmm.
once you have those distance mates set up, you can do a design study where you change them by a millimeter each and track the total rotation and translation of your wing as a rigid body from that. And so
Yeah.
from that, you can say, oh, small manufacturing errors in this rod are most impactful to the final wing position. We should either change the position of this rod, and so change the angle, or we have to control this very tightly in our manufacturing process. Does that make
Hmm.
sense?
I think I'm understanding what you're saying.
Yeah. What I was also saying is that you can also make a 6 bar system that has 6 bars in it,
Hmm.
but it would only constrain 4 degrees of freedom or 5 degrees of freedom, and you still have a
Hmm.
degree of freedom not missing because you did a bad job, right? So
Yeah, if all the
there's also a constraining way in SolidWorks also to check if all of your degrees of freedom are truly constrained.
hmm.
And I believe that's also a way in ANSYS as well. I'm just less familiar in it. I know it's super easy to check in FEMAP. In fact, it's one of the fundamental things it initially checks when it does its solver.
Hmm.
And I imagine ANSYS is too. Uh, but ANSYS, the moment you click weak springs, it just ignores it. So, like y'all could be ignoring this, large amount of play that is in a non ideal direction that isn't part of your simulations that could be
Hmm.
missing. We had that when we tried 6 bar with Panda. We tried 6 bar with Panda and we noticed that with how the frame was designed, there was no good way to remove one of the degrees of freedom without adding a crossbar across the car. And that pissed Liam off. So, so that ended that real fast. Um, so yeah, okay.
Okay.
But Charles'
Yeah,
point
I
is
see what
very
you're
good,
saying.
and you should definitely do that
Gotcha.
because manufacturing error is, not non-existent.
Hmm. Yeah, I'll make
Continuing
sure to
on.
get with Clayton and Amanda as well and like fully understand that. Thank you. And looking at that trust solver, so we actually had three different trust solvers that all came to the same conclusion. The one at the bottom one is is Clayton's. It's very similar to Johanna's. The one at the top is mine. Um, that was written in Python, and Clayton also used FEA probing to uh, verify these loads from the aerodynamic loads applied. So that is what we used to come up with our axial vectors on our linkages, and those are right here. Two of the rods are in compression, or two sets of them are in compression, and one set of them are in tension. And for the clevises, we're using the ones in within tension, as it is a much greater force. So this is the clevis FEA. A little bit conservative on the actual force. And the bolts here are 440s, which are 0.125 inches in diameter. All the bolt holes you see are actually 0.125 inches diameter, which brought us the issue with how we're going to mount the actual rod ends. First, you're looking at the factor of safety. It's at 1.6. We do trust this because this is a purely aluminum piece, unlike the other carbon fiber parts where we'd want to reach for 2. And focusing on weight savings where we can, this is one of those big things. Switching to a smaller bolt, a smaller rod, and what I'm going to show you a smaller quick release as well. So I'm calling it the cotter pinner because it's a pin that holds a cotter pin. On the right hand side is the shear calculation for it and the factor of safety I got from it, which is almost at 2.5. And the cotter pin itself is a 1/16th steel cotter pin from McMaster-Carr.
You can't use cotter
This
pins in a 6-pin in a 6-bar.
sorry,
You now open up that every one of these locations now have an additional degree of freedom, right? So they're no longer true
Wesley,
sphericals. They now have more slop in it.
so
Wesley,
this pin, yeah, the really like mallet looking shape that I brutally drew on SolidWorks is the pin that is it's actually 0.12 inches in diameter.
Yeah.
That would go into the pin, and then the cotter pin goes into the small hole at the end of it.
Right. But now you're spherical, right? Because your pin, right? Just like any bolt or anything, right? The hole you go into, right,
Hmm.
isn't, what you're putting into the hole isn't a push fit, right?
Hmm.
Please don't make it a push fit, right? People
Hmm.
will hurt you. Because now the wing's not removable at all.
Of course,
Um,
yeah.
but if you use a cotter pin over a bolt, the play that's in between what would be the cotter, if you use the cotter pinner or any other quick disconnect, right, where it's not applying a friction force from the clevis onto the spherical, you now have play between the spherical and the quote unquote bolted pin.
Hmm.
So that, even though it's small, right, we do have an arrow rule that says that should be no free moving slop, right? So if I can grab the wing and I can jiggle it and it takes basically near no force for me to do it, they could say that your wing does not qualify. So that was my big thing that I stated with the 6 bars. I was like, they all have to be bolted joints because you cannot use quick disconnects anymore, because there's now no resistance at your locations, right? And all of them, the whole system is going to have, okay, maybe it's 5,000. It's probably going to be more in order to correctly get it through the hole. But now you have, plus or minus quarter thou on each point has plus or minus quarter thou, and so every single point can jiggle.
I'm a bit confused. So like with that,
So like every single one of these bolted joint points, right,
mhm.
can now jiggle, right? The spherical jiggles within the clevis,
You're saying
right?
the bolt would fix that because it would compress the
Because
clevis
you
into
now
the
have friction on the spherical itself.
from the sides of the clevis, the internal
Yeah.
sides.
This wasn't an
Okay.
issue with the horizontal bar because the horizontal bar basically, okay, technically, if you had enough friction force, the horizontal bar only needed the horizontal bar,
Hmm.
right? And you wouldn't need the upper tie rods at
Right.
all, actually. But because, we want to mechanically lock out, not just purely rely on friction.
Mm,
we add the tie rods. Um, but we were okay with those being clevises or being the quick disconnects because really and truly they weren't contributing to that shake resistance as much as the big horizontal bar and the big honking bolt, right?
mm.
Now here you have there is no actual true compliance reducer within your system. So your system now, every single one of these sphericals now also has a non-rotational compliance. So now there's translational compliance within the whole system.
But in our in both our simulations and our calculations, we're treating it as a pin support. Whereas what you're saying with the friction of the bolt on the clevis, it would no longer be a pin support, it'd be a fixed support. But wouldn't the whole point of a six bar to be everything is a pin support?
Well, the 6 bar is you're getting the spherical because you have a spherical joint, right? That goes through
Ah,
right? A bolt goes through a sphere and you have a
mm,
spherical joint, right? But with this, what I'm saying is in between the spherical joint and the pin, right? There is
mm,
now compliance. There is now a nearly every single direction degree of freedom. Actually, there is a every single direction degree of freedom now added. Now, it is not a limitless degree of freedom, right? There is a wall, at some point it hits the pin or it hits the edge of the clevis, but it does exist. And so you will feel it in the wing. You'll feel it in the wing. And this is why, like earlier when I told, Clayton, I told him like every one of these, you have to do a friction connected bolted joint. And that's going to make installing and uninstalling this rear wing very complicated. And he told me, of course we have to, it's not going to be that bad. Now we're looking at, removing that because what was likely the statement was now installing the wing, you need a torque spec on every single bolt and to ensure that it's actually working as intended. So we've added cotter pins or the
mm.
cotter pinner, and now it's not. Now we can't. Right now we've opened up this degree of freedom again, and this
I
issue.
get, I do get what you're saying. My concern is that like the on each side of the pin it would be 0.025 inches, which is just over half a millimeter. So if half a millimeter is like or 0.625 millimeters is the degrees of freedom, is that not nominal enough to be like
No, because
disregarded?
what it's going to do is it's going to clank, and the judge can now shake it back and forth. What is likely
Mm,
probably nearly with all of the tolerances stacked up, with it being a spherical joint, it's probably going to be like 2, maybe 3 millimeters worth of how much they could shake it at a minimum,
mm,
right? Because now it's Charles's statement, right? Now you don't have linkages that are a controlled length, right? Now the length is moving,
I see.
right? Now the length is changing. And it's not like it's changing because it's a spring. It's changing with zero spring force.
Hmm.
So that now makes this a huge issue, right?
Hmm.
Um,
And other teams that do six bar, do they bolt
do
them
not
down
do
to a
no one
spec?
does cotter pins because everyone does 6 bar. What made what we did really cool, what the judges really liked, was the fact that we used the quick disconnects, and we could say like, well, our system is stable enough and how we've designed it that we can put quick disconnects and we can lower the amount of bolted joint connections within our
Hmm.
system, right? Which is really cool.
Yeah.
Not saying that a 6 bar is not cool. It's pretty cool that we can constrain things with just 6 bars. It's kind of neat. But at the same time, it becomes issues.
Hmm. I see what you're saying. I think that's something I need to reconsider.
Yeah, it's
Um,
it's it's now like now, right now everything has a compliance to it that's
mm,
non-stressed, right? I imagine, and Ryan, correct me if I'm wrong. I imagine you can add this into ANSYS, but
Add what?
add a non like add an amount of compliance around a shape
You can have
that,
Yeah.
contact clearance. It's like,
yeah, contact clearance, that's what it
but like
is.
the fundamental thing here is like what Wesley's trying to get at is like you should use something that doesn't have that compliance built in where there's zero resistance to it. So like there's other solutions. You can do like a rubber bushing or something. This is something that um, big auto OEMs will do on their control arms, right? But at
Hmm.
the end of the day, you have to have something that like provides a like increasing force that goes through zero deflection. You can't have something that provides no force up until you hit a point.
Well, and then big auto OEMs also compress the rubber bushing into center with a bolt so that there's the compliance is the rubber bushing for shock and feel because like Porsche in their GT series of cars do not use rubber bushings at all. They're all metallic bushings. Um, which sucks to like comfort. Which is why they do that. Also a like a quality and tolerance stack up reason. So like our
Hmm.
issue here is that we're not applying any friction load to the spherical joint from the clevis that's holding the spherical at the at the point location that it's rotating around, right?
Hmm.
You can imagine the spherical as a point, right? Held in space by a bolt, by the clevis. But since the clevis isn't actually holding the spherical in position, because there's going to be tolerance and there's going to
Hmm.
be clearance so that you can put the spherical into the clevins in the first place. Otherwise, you'll never get this thing in. I promise you, it's going to be awful.
Yeah.
Um, and the spheres are also not accurate. There's a little point that it will rotate around. And now by adding this, you now make it to where the point at which it rotates around also has a like a translational sphere around it. That point can move anywhere within that sphere or oblong shape.
Hmm.
And it can move anywhere around that, unconstrained, completely unconstrained,
Yeah.
right? And that really destroys the kind of constraints you have to do within a six bar. And one of the constraints is that your linkages must not be able to change in length,
Hmm.
right? If they start to change
So,
in length, then everything starts to move a lot.
mhm. So I'd have really two solutions to this. Like either A, I replace this with a bolt, which is really hard to uh like take on and off all the time, or B,
Ditch
um
six bar.
I was thinking some sort of rubber bushing that would
Nope.
mitigate.
No, it's not going to unless you can fill in between the spherical and the cotter pin
Hmm.
it with rubber, which are not, right? Because you'd have to push fit it. The rubber bushing is that's not entirely what it's for,
Hmm.
right? Like it's like they're still clamping the center of the bushing with a clevis and a torque spec. All
Hmm.
it's saying is that between the linkage and the clevis now has movement,
Hmm.
right? But the bolt, the clevis to the rubber bushing center where it's attaching, it's still fixed by the friction from the torque spec of the bolt.
Hmm.
It doesn't now have a degree of freedom, which is what you have here, is that the clevis to the pin has a degree of freedom. The
Yeah,
pin to the inner hole of the spherical has a degree of freedom all
hmm,
together. So
I
the
see.
pin could move uh, uh, the pin could move half a millimeter within the spherical, and it can also move half a millimeter within the clevis. And then
Hmm.
the one on the other side can also move a millimeter or a full millimeter in the other direction as well, right? And so now you can get huge, especially rotational changes in movement,
Hmm.
especially as this is a huge part, right? And there's a lot of distance between where the tie rod connects to the outermost edge of the wing.
Yeah, that makes a lot of sense. Thank you for pointing that out. I would not even notice that.
Is all of your linkages have this cotter pin in it?
Yes, all six of them, all on the wing side, not on the frame side.
No dear. Yeah, they're all going to have to be bolts. They're all going to have a torque spec. You're all going to have to make sure that ratchets can fit around the
Hmm.
clevises. So your clevis arms are probably going to have to be larger as well.
I see. Okay. Alrighty. Um, so after this, the rod selection. Um, I do remember what you mentioned about not trusting Rockwell's calculator. Um,
They've
this
actually
one
updated
is
their calculator. It's probably better, in all
yeah. I
honesty.
noticed that there's like they added it like last summer I think, and it's decently accurate. I think. But I think for the sake of design judges, I would definitely have to let's use like a CLT calculator on Excel. But these are some of the loads. So 222 pounds of force. 16.5 is a little larger than the largest rod, and that's diameter and the ID and OD. Um, Max axial stress is below the yield for this rod, so it would ideally work within the 6 bar situation. And this is also is the max load.
Wait, say
Uh,
that
the
again. What wouldn't work?
Oh, this would work. Right.
Okay. What's your
Yeah.
safety factor on what's your safety factor on buckling?
Um, I haven't looked at buckling because the tension was the largest. It was 3 times larger than.
Yeah, but like tension's going to be reliant on the epoxy joint.
Mhm. Whereas buckling would be the actual rod.
Yeah. Like you should still check to make sure the rod's not going to fail in tension. But if the rod's failing in tension, you're really screwed.
Yeah. Okay. I
Because
will make sure.
then you're not even looking at like, is the epoxy joint holding to the like is the carbon failing around the epoxy joint? That's a whole
Mhm.
other math issue, right?
Yeah.
But yeah, you need to look at, buckling
Yeah. Okay. I'll definitely
because
run
these
that
are
question
some
as well.
which rod number is this?
It is not on here. I do have it open in my
Because these
tab.
are quite
But
small.
when I looked up 0.25 times 0.375, there's two that come up. There's the high modulus one and there's this one. Those are the only two I believe on Rockwest's site of this size. And
Okay.
those like yeah, and I chose the non-high modulus one.
What's the I don't know. Are you doing inserts or outserts?
For this would be inserts.
Hmm. What's the thread? What's the bolt for the sphericals that are going in this? What's the bolt size?
Um, I want to assume that it's also 440, but I'm not entirely sure. I'll have to
The
confirm
440s
that.
are that they're an 1/8 inch OD?
Yes. Hmm.
Hmm.
Because we did drop the size because Dynamics is a bit rudimentary to like decide that because Dynamics is using a smaller size, we should too. But that's what we did all the validation with the trust solver and the calculators.
Yeah, I just don't know if you have enough meat on the insert
Mm.
between the thread and the bond because you're going to
Like for like
have
thread pullout.
yeah. Well, and
Yeah.
for the insert itself to fail, the insert itself might
Hmm.
fail.
Yeah. That's part of the material testing plans where we like figure out what can and can't be done with everything. That's something we're hoping to get at right as the semester starts, as we start getting orders from that we get right purchased from Rockwest last semester in,
There's a way you can check it.
like just calculating it or
Yeah. Yeah, you can
okay.
sim it, I think.
Hmm. Gotcha. And then for manufacturing, very similar to our previous manufacturing methodology. Only real change is that instead of using free coat, we're using fiberglass as fiber release. We used it a bit last year. It worked really well. It also works pretty well when used with waxes as
Why?
well. So it's a lot safer. it's water based and you don't need gloves to handle it. I remember I was using it last year and Kellen came up to me. He's like, "Hey, so wearing gloves," and I showed it to him. He's like, and he was really surprised that you didn't have to like wear gloves or whatever. It smells pretty good too. But I probably would still wear gloves because why not?
Well, it's still
Which compared to
harmful if swallowed, right? Like it says it on the label. It's not like it's, you know,
mm,
okay. This is going to be, but is it capable of standing up to temperature?
mhm.
Is
We
it
use
high
it
temp
for
application?
yeah, we use it on a lot of our aluminum molds last year on our wings.
Does it create it so it also leaves a but it leaves a non-chemical fill?
I'm not sure if it leaves a film on the part, but it can also be reused, like similar to free coat. Like it lasts for more than just one like layup.
Just be careful with it being water-based. Don't rush.
Hmm.
Like now
Gotcha.
you have to slow down
All right, yeah,
because if
makes
you
sense.
trap water within the part, you're going to have huge bubbles. You're going to have
Hmm.
porosity again. And there's nothing you can do about it. You're just screwed.
Yeah, that makes sense.
It's just the unfortunate thing of it being water-based.
Hmm. For rods, I'm thinking a diamond blade hacksaw would be pretty optimal to cut straight lines on rods, and then using laser cut acrylic jigs, especially for like the rear wing assembly with all the different rods and six rod setup, having a jig system that's been laser cut to exactly the right size that we use to cut all our rods and place them and mount them and glue them. Similar
Yeah,
to
well, they
what,
should be threaded, right? So you can adjust
mhm.
rod length a little.
Okay, yeah. So like not that makes a lot more sense. Not just having one for each, but having one that could be manipulated for each.
Well, no, I mean like you should still jig it. Yeah, it should still be on a
Hmm.
jig. But like every rod, right? Every rod needs a nut on every end of the sphericals.
Hmm.
And you can adjust them, right? Don't get a thread length on these 440 spherical rod ends that is so small that you can't place the nut in it and then lock out movement, and B, that you can't adjust the rod length. Because if
Hmm.
you can't adjust the rod length, then you're going to be screwed on your tolerance stack up.
Yeah,
Because now
that
you're
makes
saying
sense.
that we're welding
To one
accuracy
side.
is
Yeah.
good. And they're not going to, angle grind off and re-weld and angle grind off and re-weld one of these arrow mounts for you. By
Hmm.
that point, everyone's going to tell you to just deal with it.
Yeah, that makes sense. I'll definitely do that. Not deal with it, but have the the longer threads.
Did EHS
And
complain about the free coat?
no, but
Just in
considering that,
case.
yeah, also it's not from an approved vendor, so I don't know how we're gonna be able to buy it again once it does run out. And
Hey,
on top of
Leo,
that,
what release do y'all use in your lab?
Uh, our aluminum molds have some sort of like post-processed machined like the machine shop adds a release agent to it. I don't I forgot what exactly it
Oh, it's
is.
probably the ceramic release. Yeah.
Yeah, exactly. Yeah, it's some sort of ceramic. It's like a
Yeah, we
black.
use it. We use it here for Boeing. We use a ceramic release.
Yeah.
You do have to re-put it on, but I think we're making way more parts than y'all were. So, which is fucking nuts. But
is
that's
that like
besides the
the
point.
ceramic coating you put on your car, kind of?
No.
Oh, okay.
Well, yes and no, right? It's like fiberglass or like free coat, right? You apply it, it leaves kind of a slight residue, right?
Hmm.
But rather than it being a pure chemical release, it's actually a ceramic deposit that
Physical
then
contact.
like yeah, like it hardens in air, right? It has a reaction that then forms a ceramic layer that's like perfectly smooth and
Hmm.
chemically resistant.
Yeah.
So like that is what allows you to, and then you can just like do it over and over again as long as you don't scrape the ceramic,
Hmm.
right? But the moment you scrape it,
Gotta
then
redo it.
you have to reapply. The problem
Yeah.
is, unlike free coat, where applying free coat because of the base chemical that it's in, it actually removes the old layer of free coat, which is like awesome.
Hmm.
Um, you're going to the ceramic will actually layer on top of itself. So that
Ah,
can
okay.
decrease accuracy. And I'm sure this fiber release does the same thing. I'm sure that if you applied, 18 layers of it, you could scratch it off and you'd be scratching off, a layer of it, right?
Hmm. Yeah. And then for the carbon fiber, we're using the exact same prepreg we used last year for all of
Sweet.
our um, end plates and wing elements.
Have y'all
Uh,
had any success with reaching out to Solvay or Torre?
no, from the contacts you emailed me, I have not heard back from them yet.
Yippee,
I'm
cool.
gonna reach out to Evonik again, Sylvain Ostech again, um, and hopefully get something or the other.
Yeah, Oztech is
And
just machining. Yeah.
yeah,
Okay.
the only lead so far was the materials, but those might not come in until closer to the summer.
Oh, Jesus. Okay.
Yeah. Future work on the rear wing. Of course, aero validation of some sort with the wind tunnels we have at UT. Hopefully we'll be able to use this to get as much data as we can. Obviously, it's not the same as if we had the entire car running on like Peterbilt's wind tunnel, but anything we can helps compared to nothing. And also a full mechanical structural simulation, not just aero on ACP and not just structural calculations. But of course, this does need to be reworked with considering changes to the mounting situation. And it will be inclusive of all internal and external structures and airfoils. That's what we hope to present to design judges at comp. All right, Amina?
Okay, so for bodywork, nose cone manufacturing, um, some important design considerations, starting with nose cone, is similar to last year. We're going to have Zeus tabs where you mount the nose cone onto, two off of the front hoop, and then one off the front bulkhead, I believe. The ones off the front hoop are going to be like towards the sides because there's like a I don't think we can mount to the middle section. And then we will use foam molds using the Pink Panther foam. And then thank you Utsav for designing the molds. Um, but yeah, these are the molds for the body panels and nose cone. For the surfacing, we start off with the foam mold, surface it, so like sand it down, some type of like primer, styro shield, and then like a wax, and then we do our wet layup. For the bodywork, we want to do something different this year. We're trying to mesh our bodywork and nose cone together by incorporating a flange into the bodywork mold. And the way that we've gone about doing this is to print part of the body panel mold, 3D printed, and then lay up on top of that entire piece alongside the foam, the machine part, to get a nice flange that we can then align the nose cone and side panels together. But yeah, the mounting for the body panel is going to be zip ties, and then if we need be, we can clamp or bond like a 3D printed arm to the frame. And then to mesh the interface between the body panels and the nose cone, we'll have some type of like dual lock mechanism or like a Velcro to seal that boundary.
Yeah, I use dual lock, not Velcro, because Velcro will get damaged with environmental exposure.
Gotcha. Okay.
Um, I'd just be careful with these zip tie mounts. We've tried them in the past and they didn't work. Doesn't mean that in the future they will work again. They won't work again, but we had it to where the adhesive isn't strong enough.
Okay.
It doesn't do well with vibration. Now you could replace the adhesive. I also think it's the release agents we use on our inside of our body panels, has a residue. One, two, our body panels are super, super, super thin.
Mhm.
So so it like peel. It's so easy for the body panels to like immediately move themselves into a way that it peels the adhesive, and no adhesive really is going to work great and peel. You could replace it with like VHB, and like VHB is like the I want to perma mount something,
Okay.
like foam adhesive. You could try, but the safe bet always is, if it doesn't work, you can always drill a hole through the body panel.
And then zip tie it that way.
Yep.
Okay. Gotcha. Okay.
Yeah, I like the 3M. What do you have? I'm unsure about um clearance mountability for this nose cone, with how it's been split. I also don't see the picture that I asked for, where it has the nose cone and bodywork transparent overlaid on top of the frame, so that we can see where the split is in relation to where the frame is. Because
Mhm.
otherwise it's just kind of hard to see. Because like all you need to do is split it at the front bulkhead, right?
So we made the split according to where front wing mounting was going through. So we
Oh
could,
yeah, your front wing mounting's weird. It doesn't go to end plates, so it goes more
yeah.
forwards. So
So
you
we
have
had
to
to
cut
push
this out.
the split line more forwards because it would interfere with nose cone, like taking
And
it
Tisk,
off.
also higher.
tisk, 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 tisk. That's the beauty of moving them outboard. Oh well. Okay.
And then side pods, again, I think I mentioned this in PDR. We want to continue doing what we've been doing in the past. Except one change is going to be that we're going to mount side pod to body panel using like properly like design brackets that follow the contour of the side panel and the side pod tucked beneath. So yeah, it would mount the side panel would mount to the bodywork and then it would also mount to like the lip, which
The
connects to
definition properly designed. Explain.
as in
How do you define something as properly designed?
In this case, it would be following the spline curvature of the side pod, whereas in the past it's just an L bracket.
Okay, we did the L bracket in Panda and it worked great.
I mean, this is more of reminiscing on the previous years. Like last year's L brackets did not do great. They fell off the car. We don't even know where they are. So,
wait, I'm
uh,
curious how much since we're gonna 3D print the mold anyways, how much harder is it gonna be to like wouldn't it just be better if you're trying to improve the like the surface of your L bracket?
Well, like for Panda, we just laid it up on an angle iron. It was straight. And these are, I guarantee you, the exact same side pods that we've been using since Panda.
no, since Badger.
But Badger had nothing different from Pandas either. Was there a difference between Raccoon and Badger's side pods from a design standpoint?
No, but um,
I know we're using the same mold this year.
yeah. The side pods are same since Badger, but not Panda is what I'm saying.
They're the same. I thought they're the same general exterior surface because they were the same to Raccoon. And then I thought from Raccoon to Badger, we made no change.
Yeah, I'm talking about Panda, not Badger or Raccoon.
Well, but Panda to Raccoon, there was no change in side pod. Raccoon to Badger, there was no change to side pod. Badger to now, there's no change in side pod, which means that from Panda to now, there's been no change in side pod.
Am I tweaking or am I just getting the wrong meaning here?
I am completely unsure. I'm saying that for the past 4 years, including this year as one of the years, we've not made a change to the side pod design. It's remained pretty consistent.
Okay,
If not, is
this is like
identical.
an unnecessary point, I think. But
Right. But what
anyways,
I'm
yeah.
saying is we used flat L brackets for Panda on a curved surface. It was a little finicky, but it's not hard to do. You can't have massive L brackets, right? We just had small L brackets and then we bolted through them with a nut plate on the other end. And then we riveted and bonded them to the side panels.
But we can
Yeah,
make it even smaller. It just
do you,
along the contour. That's the only difference. Which
yeah,
shouldn't
there's a difference.
But why?
It's because if you're not following the contour, your L bracket is not actually sticking properly to the surface of the side pod. And that's primarily the reason why raccoons' L brackets fell off. Is because the bond came off and the rivets also came off.
I'm impressed that the rivets came off because Panda's L brackets, other than the fact they were too thin and a lot of people broke them from them being too thin, Panda's L brackets are still on there.
I mean, yeah, but ours came off, so.
Yeah, well, that sounds like a manufacturing issue, not a design issue.
Okay, but these are two different side pods, Wesley. Panda had a different side pod compared to what Raccoon had. That's what I'm telling
I'm
you.
saying no, they don't. I'm saying, in fact, I know they don't.
What do you mean? John literally made a new side pod on Badger's ear. We've been using the same side pod since Badger. It's the third year that's been using the same design. Panda was a
Yeah.
different side pod.
Okay. Okay.
Okay,
Continue on. How are you mounting to under tray on the bottom?
you're not mounting to under tray
Okay.
because we don't. This is a long conversation we had with Arrow, where they don't want any type of bolt to go through like the outside flaps. So there's no mounting to under tray. And also, we don't want
So
side pod taking any of the under tray load.
has Arrow put like a 1/10 of an inch slit underneath the side pod on all of their simulations, or are they still surface meshed? Cool.
Yeah, that's a
So,
do you guys simulate
The fact that there's going to be a huge
that there's separation?
there's going to be an air gap between the side pod and the under tray.
I mean, that's the whole point of us incorporating under tray, um, what do you call it? Under tray's geometry into our side pod profiles.
Yeah, but if you don't mount it, there's no way that you can control that as the under tray deflects or as the side pod deflects, that it's not going to open up a gap. Because the side pod's not like perma mounted to the under tray, right? Like it's not like bonded in to the under tray. So if there's no
Yeah, I mean, it's a
mounting,
fair point, but
yeah, like there's gonna be air loss, right?
Can we seal it with like tape?
it's possible. Yeah, like there's ways we can seal it other than having to mount it because the main reason we are against mounting side pod and under tray together is because of the fact that it makes removability more annoying. And on top of that, you have more bolts sticking to your under tray.
Yeah, but you can have it to where you have rivet round heads on the bottom of the under tray. And the under tray
Uh,
mold is not going to be that accurate or that smooth.
I feel like we can deal with the sealing issue just with like some like like we were planning on using like what was it called? Well, gaffer's tape? Is that what it's called, Emil? Or something like
Aluminum.
that. Or like there's like surface protection tape, something like that. So
the
we're
arrow
looking
tape you
into other
mentioned?
alternatives instead of having to do L brackets because they have a good tendency of just coming off our car. especially with all the kicking of air parts and like the way it's handled
Well,
in general.
the answer is don't kick it, right? If a driver keeps kicking aero parts, they should stop being a driver. I don't care.
I mean,
But no,
it's like
treat other
hard to
people's
do.
work, right? Treat other people's work with care, right? I don't go around and hit the driver with a hammer every time they pull into the pit, right? So, you
Yeah,
know,
I mean, it's like, but it's unavoidable. I mean, this year our pitot tubes broke, so like it's like people can take care of them, but it's still inevitable. So
yeah, yeah.
yeah,
So, yeah, well, then we just increase the thickness of all the part, and then we say that the car will not save weight this year because people are dumb, right? You pick your battles, right? But what I'm saying is you're going to have I don't remember what the aero rules are for bodywork and bodywork kind of being loose. I don't I don't know what the judges are going to say about that. And that includes that. And then like, how are you fixing this air dam to the under tray? Like, are you saying that this whole huge piece, completely unfixed to the under tray?
no, the air dam will have to be bolted in, but
Okay, so there is
the
a
rest,
connection. So I don't know. I'm looking at a part and I'm saying like, where is this connected to under tray, right? If none of it's connected to under tray, then this whole thing can flex independent.
yeah,
Well, that also depends on under tray mounting, right? If you have mounting supports in the back near the air dam, you wouldn't connect it.
Well, the statement was that this isn't connected to the under tray, but is it, right? Like, I don't know.
But like it's
I'm relying, this is Charles's statement of like, I only know the information that I'm given, right?
yeah.
And what I was given was the side pod, what I'm looking at, and including this air dam, are not connected to, this is not connected to the under tray in any means of the word. So,
Yeah, I think late in one of the later slides for under tray mounting specifically, maybe
yeah,
revisit this because I think we
yeah.
do hit some of the key areas of mounting. But
Okay,
Yeah, I do get where
cool.
you're coming from though, Wesley.
Yeah. How are you attaching the tabs to the side pods?
we're gonna bond them
So,
both through.
okay, bond to side panel with rivets, I'm assuming.
Yes.
Yeah, just make sure you use enough rivets and you bond around the rivets. And then, just general good work. Um, and then you're going to bolt through the top of the tab,
Mhm.
I assume with a nut plate.
Yes.
Cool.
Okay, so this is a new thing that um Aero and Composites have kind of taken on, which is the control arm covers. So this will mainly be like a split in half type situation where you have um your control arms covers that come in pairs. They're gonna be split on a top and bottom section. They're gonna be clamped together around the control arm itself. Um, and essentially constraining all degrees of freedom because your clamps are gonna constrain any translation, and then because there's two together, you're gonna constrain your rotation. So this will just be a 3D printed piece. Yeah.
Why would we not? Is there going to be any adhesive in it?
Are you talking about
Like
it's
bonding
not
the
the
going to
two
be
halves?
bonded onto the control arms because
it
they
has to
need to
be
be
removable.
removable.
So it's gonna be clamped down
Why?
or bolted through.
It's because Dynamics wants to inspect their control arms just to check for cracks or anything.
And you're going to have crack progression on the edges, not really in the center.
I mean, I'm just
And
telling you what I've been told, so
you're
Access to
not gonna.
unsprung. Access to unsprung. You're putting in a bunch of blockages.
Yeah, yeah. Well, you're putting in a bunch of blockages, right? This thing's not gonna be easy because your trailing edges are gonna fall apart and your leading edges are gonna come apart, mattering on where you put your bolts. Like the real way to do this is to bond it, right? So that your leading edge and your trailing edges like stay together. But then sure, you can't look at the middle of the control arm, but that's not really that big of a deal. If you're going to have crack progression within these control arms, you're going to have it's going to be caused by two things, and they are each going to have separate areas. You're going to have either huge crack progression within the unidirectional on the inside of the rod, or you're going to hit such a big rock that you cause a crack through the woven structure on the outside. And that's going to primarily be issues around the inserts. And it won't matter in the center because you've had these huge freaking wings. So it's not like it's going to get hit by a rock. But yeah, no, it's going to suck for accessibility to the unsprung. But otherwise, right, like it makes sense what I'm saying. You're going to have the front and the front edge and the trailing edge of every single one of these elements is going to open up from air pressure.
I mean,
Yeah.
unless they're taped.
Yeah, the tape's not going to do that great. And our other statement that we were given as a constraint from our management was that to not make our parts look like shit. If we just are taping over everything, it's going to start looking like shit real fast, right?
Yeah. I think this design is still relatively like new, so we need to fully fledge it out.
Yep, nope, that's
We
fine.
try to get into
Just wanted to bring that up because if you're
yeah.
just going to bolt you're going to have problems. Like my recommendation is my advice is going to be run right now and do a analysis and do a thought process analysis on you know these being perma mounted bonded together. Now they don't have to be like super perma mounted. They can be like urethane bonded. So it's kind of like you can, cut it off with an X-Acto knife pretty easy, but like assume that they're basically not removable without it needing to be like 24 hours.
Okay.
That would be how I run them because that's going to give you the best looking, best performing, lowest weight, most accurate to arrow option.
Okay. You said semi-removable bonds?
Yeah, like you can use a urethane adhesive. It's quite forgivable. Urethane adhesive is quite forgivable. That's what most automotive uses if they want it to be like permanently mounted, but at the same time, there is small cases where from a maintenance standpoint, it might need to be, removed.
Got it. Okay. Yeah, that helps a lot. Thank you.
I would also use urethane on your which is actually that's probably why your L brackets failed. Use urethane to your body work for any of your bonds for your brackets
Oh, okay.
because the urethane has a higher elongation to break than standard epoxy, and I guarantee you y'all didn't use urethane last year because we forgot to buy it.
Okay.
2 core 2.
I don't know if you have something to say other than this,
Yeah.
but jump in.
Here's an
Forgot
under
about that.
tray.
Yeah, I have questions. Do you guys have any plans for mitigating like resin overflow and like saturation of the core? Because that's kind of been a topic in past years where like the under tray gets made and then it's really, really, really heavy and kind of blows out mass estimates. Um, yeah, I'm just like wondering what you guys are planning to do for that.
So,
You go ahead.
sorry. Okay. So one of the kind of spearheads of the season is trying to incorporate resin infusion. Um, and that could be something that we could potentially look into from better managing epoxy and saturation.
Okay.
Yeah, the issue, so the issue with under tray is that we've been doing a wet layup, and because it takes so long to lay it up, our like first initial couple plies always end up like the epoxy is curing, so you don't have the, so that's one issue, right? So you can't push that epoxy out, right, with the vacuum into your breather. And then the issue two is that last year, last year had a whole other issue of mixing ratios, and the year before had a time issue, and the year before that had sorry, last year, the year before last year, Badger had um, had mold quality issues, and then our first year Panda was just time. So it's just such a massive mold. It is going to be hard to maintain time, but with resin infusion, it's just now your mold has to be perfect.
Yeah. I guess I have an idea on this. I'm not sure how feasible it is. Like in terms of taking your core, can you then add a like half millimeter thick sheet of like polyurethane or something and like
No,
heat shrink it around?
no, dear God,
Or
no.
okay.
So
Is
so
there any
the issue isn't that epoxy's going into the core. That's not that would be an issue if we used honeycomb, but we don't use honeycomb.
well, Wesley, the undertrays have consistently ended up
Yeah, no,
several
that
pounds
it's
heavier, right? So like
yeah,
where is the
it's
epoxy
the
going?
it's literally it's the parts are like, because we don't have a thickness control, right? Like we can't control how thick the parts are in wet layup.
Okay.
Wait, sure. Also,
So
just to put it out there, we've never like this year we're trying to do a full undertray core, not like just like the flat plates, because in the past we've never done a core on the full undertray.
yeah, actually Pandas was had no core at all, right? And then
Yeah.
the outboard plates on Badger had core, and then I believe Raccoon had a little bit extra of core, but it had
It was on the
it had
sides
another
only.
issue. Yeah, was it still only on the flat plate areas? Yeah,
Yeah,
so we
only on
really
the side.
actually don't have a lot of core. So it's never been that we're filling core, and because we use foam core, it's never really that big of an issue. What we do get excess epoxy from is because it's curing before it's getting to like its cure point, not its final cure point, but like it's now super thick cure point. I don't remember what the name of it is, but it's getting to that point before we even bag it on the lower plies. So our resin to fiber ratio on our under trays are really bad, and so that leads to, and because we're not like, it's not like we're decreasing the amount of fiber we're using. We're just it just ends up with a lot extra epoxy in it. So that's why we have had mass issues with under tray. It's such a long layup because it's such a huge part. It is an ungodly large part,
Okay. Um, like
but it's a good concern to bring up.
I don't yeah, like can we talk mitigation methods for that then? Like having an epoxy with like a longer initial set time
Yeah, we
or
that's what we use the longest set time we currently have available to us.
can we
Um,
maybe look at like
that's what
begging
resin
someone
infusion.
for a walk-in fridge or something? Like
That's
slow
not
down the
gonna
set?
it's not gonna do enough. Um, without like, really and truly, your option is to do an infusion, which is going to get you an even better resin ratio, anyways. But it means that you can spend all of your time laying up the fiber. It's just going to cost more in the tooling. And then option two is doing pre-preg, where you have an even better resin control. It just, you need an oven or an autoclave, and you also still need that good tooling. It's just the nature of wet layup and how big this part is. The other option is saying like make the part smaller, don't do as big of an under tray, and that's not really an option.
Blow my shit off if I came out and said that.
Yeah, yeah. Which is why I said it, right? Yeah, but those are the options, right? And they're it's kind of it's just the under tray is an unfortunate part. But I get it.
Yeah, I
You're
guess
right.
that's that like that's that horse beat to death, right? Like we have our options. It's a matter of like you said.
Money.
Well, I think Amaya said looking at resin infusion was on the
Yeah.
table. Like it's just a matter of like trying to speedrun how quickly can you prove out the resin infusion process then, and like
Yeah.
make the mass estimates less bad.
Yeah. And you actually would end up with a stiffer material
Yeah,
overall.
hello. Can you guys hear me?
Yeah.
Yeah, sorry to interject, but that is part of the R&D project. I was looking into resin infusion. All of these implementation plans and timelines have been written out, so I feel like I can go into more depth on that when we get there.
Yeah. Is there a cost analysis between resin infusion and prepreg versus structure and weight for this part?
There's not a structure and weight analysis. This resin infusion the project was spearheaded almost 2 weeks, 3 weeks ago. So
Well,
I
we've
have
been we've been talking we've been talking resin infusion for 4 years now.
Oh, that's awesome. Um, I have documentation. I have documentation that I can upload and then look into it. But as of currently, I have like obviously resin infusion. If that's been a plan for 4 years, I think I can work with you to understand why it hasn't been implemented to the scale. But currently, we have ordered the beginner toolkit from Easy Composites that we're planning to use. So
Yeah.
yeah,
The yeah. We'll talk about
yeah, we'll get
why
there. Yeah.
we ended up not we haven't done resin infusion yet. We'll talk about that.
Awesome. Yeah, looking forward.
Cool.
Okay. So for under tray mounting, kind of we were talking about before, we plan on having multiple mounting locations across the under tray, particularly uh, one having a tie rod after the driver that's going to be in the location next to the air dam from the side pod. So realistically, even if your under tray was not attached to your side pod, with maybe like some rudimentary like sealing with tape, would you really need to bolt into your side pod, Wesley?
It's just not going to be. It's going to be a very compliant joint.
Okay.
Right. Because the under tray is going to move and it's the moment the under tray moves in respect to the side pod, you're putting the tape in peel, right? So if that center part goes down, the tape that forms an L on top of it is being pulled in peel. So the tape's going to do nothing, right? It's just going to peel off. And then, heaven forbid, the tape comes off the car, and then now you're disqualified.
Yeah.
So
what do you think? Do you think we just put a bolt through the air dam?
Well, you might be able to use click bonds. It's going to be funky. It's going to be funky. I would have some way to mount to the under tray. I would have some way to mount the side pod to the under tray. I wouldn't leave it up to tape. I really wouldn't. And I would ditch the tape and either just admit to Arrow, and Arrow just needs to run the like a tenth of an inch gap in between the side pod and the under tray for the rest of their sims, or you find a way to physically mount it and then you can add tape the seal. But I wouldn't just leave the tape because you know, Ryan will be, Ryan and the rest of the team will be really pissed at you if a piece of tape comes off during endurance and so it disqualifies you. Or heaven forbid, a piece of tape comes off during autocross or skid pad and then it disqualifies you for the rest of the race. That that is a bad. Like don't do things because you're worried about a single rivet head underneath the under tray or because you're nervous about bonding to the top of the under tray, like do the math and like do the work, do the engineering. um like don't risk just tape. It's not worth it, and it's going to look like shit. Any tape
Mhm.
that will at least look half decent is not going to be strong enough, and any tape that is going to be strong enough is going to look bad.
Yeah,
So
that makes sense.
judges ask less questions when the composites look good. It's hilarious. It really is. Like first look appeal really does help your car. Really does. Our cars have consistently looked less and less good since Panda, and we've kind of consistently not been as close to design. We've actually done pretty good design final wise, but like you can look like when our cars looked the best, we were close to design finals.
Yeah.
Panda, we were right before the runner up, right? Like that car had a ton of design problems, but it looked great, and we had a lot of good reasonings, especially from the aerodynamic side.
How would you feel about maybe incorporating like a plate into our layup so that we can avoid maybe sticking both through our under tray? If we,
Yeah, like you could like put an L bracket within the layup.
yeah, yeah,
You just have to make sure that you cover it in enough breather that it doesn't poke through the vacuum bag.
yeah. Wait, how do you ensure that it's not gonna like delaminate or like the plies aren't gonna come apart?
You just make sure you have it's inside the plies. It's
Okay.
inside a consistent ply. So when you have your big sheet that you're going to lay out, you cut a slit in it. So you have discontinuous fiber at the slit, but
Yeah.
otherwise it's full continuous and the fibers go all the way throughout the under tray, right?
Yeah.
It's basically like you're doing an insert, which is also something you could do.
Hmm.
You can just have like a not all the way through insert.
Now that I'm thinking about it, if we kind of do like the halfway in the under tray, then we can maybe get behind the or get around the issue of having like a bolt stick through your under tray, right? When you mount to the side pod.
Yeah, it just matters how thick that area is.
Yeah, yeah. Okay, cool. But besides the tie rod, we have two areas for tension cables. So like steel tension cables, that's where the eye hooks are. They're gonna mount to the frame. The one in the front, um, or like near the driver's side is gonna mount to right in front of the side pod. So last year we did tie rods and apparently it was a lot of issues with like mass flow into the side pod. So now we want to switch to something smaller, which is cable. So
I don't know. I never find cable doesn't look professional, right? Like tape.
okay.
How are you not threading these through the under tray? How are these attached?
The eye hooks,
Yeah,
yeah, we would thread them through, but we were thinking if there's some sort of like mechanism to not have to thread them through.
that's
Whether,
gonna be really hard.
okay.
And like right, like well, how thick is the under tray there in the rear?
2 core two, so 0.244.
Yeah, you really only have the core, which is like 0.2 of an inch to put anything like thread or what have you. I guess you could do it like a key slot, like what you see on like the back of extension cables. I was just thinking about that
Oh
for a
What
yeah,
if
yeah.
side
it's like a
pod.
base plate? Like you have like a plate and your hook's like attached onto that or something.
Yeah.
I like the slot idea. That's kind of cool.
But how do you attach the hook to the plate?
Yeah, no, I was just asking if there's like a part like that.
Yeah, like you could like thread the plate, right? Which is what most companies do, most people do. But there's not a lot of, you only have like 0.2 inches worth of thread. It's not really a lot. My other issue with cable is like, have you put 50 pounds or like, have you like sat there and like tightened a cable to how much we usually tighten a cable to, and then put a load cell on it to see how much tension it's pulling, and then put that at each of these cable locations and see how much deformation you deform the under tray just at like static right height.
Mhm.
Because the reality is with two core two, you're probably, and I assume that it's not the whole thing's not two core two, right? Only
The
small
mid-
flat portions of it are.
No, the middle section entirety we're planning on making it two core two.
Are you thermal forming?
What do you mean, like?
Are you thermal forming the foam?
Oh, yes,
Yeah,
yes, you
we'd
would have
have
to
to.
somewhat bend the foam. Yeah,
Yeah, well, you have to thermal foam it. You can't just cold form it because then when you pull off the part, it's going to try to go back to nominal,
and you
right?
would
So
do it before you put it into the oven. Like, okay, I see.
well, y'all can't. Well, if you,
Oh, right, sorry, I'm getting confused.
yeah,
Yeah, that
that's the
makes
nice thing about doing pre-preg is it like also
sense.
pseudo relaxes the foam as
Yeah,
well. Oh, and then you can also use honeycomb, which just doesn't care. Um,
you said honeycomb traps the epoxy, right?
yeah, so you can't use it for wet and you can't use it for infusion, but you can use it for pre-preg because the epoxy doesn't really flow into it. And usually you also put an adhesive sheet on it. So you have a little extra epoxy to like form some gaps, but you're not filling the honeycomb.
Okay.
Yeah, I would try the keyed slot, but I was thinking about that for side pod as well. Like you can have like a keyed slot and then you just bond the bolt in. So like it was keyed so that you can get it in, but it's not really keyed so you can remove it. Like it's so that you can get a threaded stud in that's within the laminate without having to that would be really you'd have to machine it. Oh, never mind. That kills that. Ah, no, wait, you can fill it with oh, you could fill it with wax. Oh, okay. This might have to be a conversation for a later point. I'd just be nervous with cables. You're going to deform the under tray from its nominal position, and it will never go back to nominal position, no matter what speed you go.
Okay.
Because the under tray really is not like under trays really do not make a large amount of PSI. They're purely relying on the fact that they're so massive, on that's how they make so much downforce. Right?
Yeah.
But you never really have, especially in the diffuser area, you're not going to have a lot. That will be near to pretty close to, it should be close to atmospheric from a theory standpoint. It doesn't have to be. That's what we did in Panda, but like it wasn't in Panda. That's why we had the beam wings. But yeah, so I would just be careful. Um, looks good though.
Yeah.
Bootsoft, did you do under tray?
Yeah,
Looks good, man.
thanks.
Okay. Mold. How are you doing those curved plates on the side? They're just going to be independent curved plates you bond on.
Yep, exactly. It'd be a separate layout.
Cool, sweet.
But yeah,
Yeah, a lot of funky shapes on this guy. A lot of clearance locations. A lot of random clearance locations. Man, that fucking sucks. What's your runoff? Do you have any runoff?
so explain that again.
Like you don't have anywhere to put a vacuum. Like you're gonna need a lot of space to do infusion. Like you need an additional like 3, 4 inches around the mold
Hmm.
to do infusion. Right? Because you have to have the tacky tape, you have to have usually either a vacuum or a resin line, and then you have the beginning of your mesh and the beginning of the peel ply, and then your carbon.
Yeah.
Okay, wait, we might have this space like okay, like last year we did the undertray in like an envelope bag layup. Basically, you're like so you will have theoretically a bunch of excess space on the sides of the undertray
Right,
behind the side.
but for infusion, you can't do envelope. It has to be a solid pull. That's one. Two, you're using foam, so dear God, please don't ever do an envelope. And then three, because you can like compress the foam and distort the foam. And then three, the infusion's really relying on pulling through vacuum to lay up, to infuse with the epoxy, right? So like you can't really think you have to change how you think about the mold compared to what you do for wet layup, right? You have to change how you think because you're using a different manufacturing process, right? Pre-preg, you can do your molds pretty similar to how you do wet layups, but infusion is really funky in how it works, and so you have to be really kind of careful.
But we can do pre-burger. Does the undertray fit in the oven?
No, but it
No, right?
might fit in UT's autoclave. And a pre-preg undertray would be way lighter and likely wouldn't need cables.
If we had the other mold from Celine, and it wasn't just a block, could have maybe tested it.
I can't
I mean,
believe
we
they
can still make
shipped
a
you a
block, I
block.
guess. It just won't show us much.
Um,
But yeah, some future
y'all
work on
haven't
that.
ACP'd it?
No, 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 no.
Oh, so that 4-core Ford's gonna go way fast. Yeah.
Yeah,
Okay.
we need to. That's something we need to like focus on.
You need to change your material models for
Wet layups.
wet layups.
Yeah,
Interesting.
we need to actually get some material data from material testing, which we haven't gotten.
You can just use rule of mixtures.
Rule of mixtures. What
You can
is
use rule of mixtures and you can use the fiber resin ratio rule. What I taught in the CLT lecture, where it's the modulus changes based upon the modulus and volume percentage of the two different materials.
I
okay?
think I remember talking about, yeah, I'll have to like revisit it to refresh my brain.
It's the one that's linear and then there's the one that's kind of parabolic. And then
Hmm.
you say like, well, it's somewhere in the middle.
Got it.
Yeah.
You can use that to make an assumption. So like your pre-preg, you're usually sitting at about like 30%, and then normal wet layup, you're usually sitting at like 55 to 60% resin, and under tray, you're probably sitting at like 70, 80%.
Hmm. Yeah.
So just like, and then infusion's always going to be at about 50. Usually it's about at 50 to
Okay.
55. So like the statement is always going to be, well, the pre-preg's better. It's a stiffer and lighter assembly and stronger assembly or material just from a basis, just from pure fundamental. But it can be costly. Now, if you do this out of infusion, it can also be very expensive for mold material. Like the only reason you do infusion is because you don't have access to anything that can do the temperature needed for pre-preg. But you do have access to things that can do the temperature for pre-preg. So
Hmm.
and there you go. There's the story why we don't do infusion. Because the parts are either so big it's too expensive, or it's just Prepreg's better.
Yeah.
Okay, cool. Yep, beauty answers. Research projects, material testing. Yep. Upcoming dog bone coupons. Well, they're not dog bones. Please don't shape them as dog bones. Um, okay, you really need to look at the American Standard for Material Testing stuff.
Okay.
I wouldn't do like we said before, I wouldn't do like the 6 core 6 and the 13 core 6 for monocoque. Yeah, that's an FSA rule that we have to meet. But doing 3-point bends to look at like material testing um for like wings and under trays and all that type of stuff, unless you expect your load to be in a 3-point bend,
Hmm.
I wouldn't do it. I wouldn't do
Yeah.
it. Buckling sim's pretty easy to do. I just throw it in. Or a buckling test also is pretty easy and pretty fun because usually you break the metal before you break the carbon. Yes, you should repeat these tests every year. You have to. It's the rules. 16 coupons. Yep. I would test just the carbon, then just the core, and then I would test the shear failure between the core and the carbon.
It wasn't been bonded together.
And the bolt pull out of
Mhm.
the sandwich panel.
Okay.
Rock West, standard coupon sandwich panel, bending. The bending really doesn't give you a ton of information outside of just a 3-core 3, a 6-core 6, and a 13-core 6, 13. And if that's just for monocoque, you just have to do that for side impact zone because they're like saying like, well, what if your chassis slammed into a pole? And then you're looking at energy absorption. You're not really looking at um you're really only looking at load over displacement. That's all you're really looking at because you're looking at energy absorption for
Hmm.
19 millimeters of deflection.
I see. So that
And then
wouldn't
yeah, for
instantly.
steering wheel, you'd get more worth out of doing the base material testing.
Hmm. That makes sense. Yeah. Okay.
Ooh, wind tunnel testing.
Okay, so the wind tunnel testing has been in the books for a while now. Admittedly, I just we just need to figure out what airflow we're going to use. So the second this semester, we're going to hit the ground running, figuring out what airflows to use, what airflows to test, and then we'll send Bogart the final um, documentation or like the testing plans. So it's just a matter of sending them out and making sure that we have everything together. So we can go through the document again, like after this or another time that works. But right now, like we know we're going to do this. We just need to get it done at this point.
Yeah, my recommendation would be to use the metal molds, do a cascade of 2 of the secondary element.
Okay.
Because we're not using that front wing mold anymore, are we? That's not on car this year.
Not this year.
No.
Okay, I wouldn't use it. I would make a single wing element that's just independent. Um, that and then I would make 2 wings. I would test one that's just a single wing and another that's in a cascade, and I would make one set where they're both 2 ply, and I would make another set where they're like 13 or literally however many ply you can fit in the mold, make it that.
You were thinking just like 3D print it.
Nope.
Don't 3D print it?
Nope, because you want to check surface quality. That's a whole other thing, right? Because the 3D print's not going to have as good of surface quality, and that's going to affect your parts. That's
What if
going
we
to
have
affect your arrow. So that's another test. So then
but
you
what if
would
we have a carbon skin around it, like so the surface is the same?
nope. because the surface is from the mold, right?
Hmm.
Not from the bag. Like you have to make the wing exactly like how we make it, or you're adding too many factors in, right? There's already a ton of factors in, right?
Okay. Yeah.
By laying up, by skinning, by like the technical term is skinning the part, you're
Mhm.
adding other factors in as well, right?
Yeah.
And then how do you know that exterior surface is accurate?
Well, I would assume you would test the same, like you would use the same surface you use for the like the two ply, and then you would just put that on like a 3D printed part. Like you would put that surface on something else
Yeah.
to try to mitigate any
Like
like
put something inside it.
yeah.
Yeah, you can. It's just not um you can do that, but you still need to run a structural analysis that's super intense on a 3D print, likely FDM part.
Okay.
Because it's going to deflect, right? But you're just trying to make it to where the deflection is marginal but known,
Yeah.
right? It's marginal but known, right? Like if I say it's 12 ply, right?
Mhm.
I can run a sim, assuming my material testing's good, and it will output how much deflection it should see. And it might say, I expect to see 1/100th of an inch, right?
Yeah.
And I can go, it's known and very marginal, right?
Yeah.
But it would be really hard to run a simulation on a bonded in internal structure and say that it's not deflecting, right?
Yeah.
Because the reality is, I think you're still going to see quite a lot of deflection on the trailing edge, even if you do a large ply count.
Yeah, just because that's the weakest portion.
Yeah.
Yeah, that checks out.
Um, yeah, yeah, definitely feasible for this year. I would do secondaries, and I do them with the metal molds first, and then I do a 3D print mold second, and then check the differences because there's gonna be differences.
Yeah.
Hmm.
For sure.
I don't know how drastic, but it's gonna be quite noticeable. It's gonna be quite
Yeah.
Hmm.
gonna be noticeable. Um, so
But alongside wind tunnel, we can definitely work with Arrow to figure out how to take the deformed geometry, like I know you and Leo were saying before, and have it output like a CFD and then get a delta value between like what the actual CFD value is, or what the actual value is and like what the CFD value is. And then you can examine deformation and performance drop off
yeah,
with
just make
just
sure you're doing that with the 13 meters per second arrow force
gotcha. Okay. And this can
because
be at no cost. It's just a
yeah, it's
matter.
a no cost. Yeah,
So
that would actually be something to do within the next like week or two.
yeah, 100% agree.
And it would be a good add-on to this just for future year reference for everyone, all the generations that are here, to have like, okay, this is what we expect. This is our safety factor to failure on the wings. Here's one picture of it. And then here's another picture of deformation at 13 meters per second, because that's what matters to car performance.
Hmm.
Yeah.
Yeah, I never thought about that too. You mentioned it.
Yeah,
That's something we gotta
that's
keep in
where
mind.
Arrow puts their force until they change that. You know, that's where deformation matters. And that was our statement for Panda. It was like, okay, yeah, like at max speed, yeah, okay, the wings deform. They deform a bit, right?
Hmm.
That's noticeable. Like 10th of an inch is a bit. It's noticeable. But at
Yeah.
13 meters a second, they were deforming like I think it was something like 6 or 7 thou.
Yeah.
And we were like, okay, or no, it was like 20 thou. And we were like, we're not the welding's not that accurate.
Hmm.
Right. The wing
Yeah.
placement in space is not that accurate. Don't worry about it. Right. So that was our
Yeah.
answer was like, well, like sure, yeah, it would be great if the wings didn't deform, but where we're actually deciding it matters deformation wise, at what speed? So at 13 meters a second, if like the wings are deforming, because what's 60 Utsov, what's 65 miles an hour in meters per second? What, it's like 29?
9.
Yes,
Okay,
29.
so you're over double. Technically, force is velocity squared, right? So we'll say 5 times less deformation. So are you now saying that the whole car, has not a single tolerance that is greater than was probably somewhere between 18 to 20,000? The answer is no. So like that's kind of that's another good reason to add to your retinue.
Hmm. That
Cool.
makes
Yeah,
sense.
looks
Yeah.
good.
Alrighty. Achit, would you be able to go over
Yeah.
resin
All right.
fusion?
Yeah. Hey everyone. I'm Achat. I'm a composites member. This is going to be about resin infusion. So I know Wesley mentioned this, but I'd still like to go over what my thought process was for implementing resin infusion. And at the end of each part, I'll be open to questions. So that way we're able to keep this concise and we're able to extract all the meaningful information out pretty fast. So with our status quo, we have two main ways to do it. It's pretty clear: wet layup and pre-preg. I do remember Charles mentioning that because of wet layup in the under tray, we result in like because of inconsistent resin like spread, I guess, it's caused a lot of issues regarding weight and mass calculations. And that's what we're trying to fix. We're trying to be as efficient as possible without resulting in extreme costs. So we wanted something that's convenient and something that's extremely effective. On the other hand, we have prepreg, which shows variability because of time sensitivity, storage constraints, and inconsistent consolidation. In that sense, I know Wesley already talked about storage constraints not really being an issue, and I'm open to learning more about that because honestly, we haven't thought about implementing resin infusions until very early. So both methods depend heavily on operator technique, and considering how the new batch of composites member hasn't even like gotten a facility yet, we want to make sure that we have something that's extremely convenient for us to implement these programs. That being said, I'm open to any questions regarding my interpretation of the status quo.
Infusion still requires skill to do. It's not an easy process either.
Completely understand.
Because your vacuum bag has to be like, okay, when you do an autoclave, your vacuum bag has to be perfect. When you're doing an oven, it doesn't really have to. When you're doing an infusion, it has to be perfect. Like you have to do a drop test. You have to like everything has to be perfect. There is still, it doesn't mean that there's no operator technique required in a resin infusion. Um, Out time sensitivity for pre-preg, that's not as big of an issue for us because we're now just buying pre-preg rather than waiting for it to be donated. So just like don't leave it out. Don't be an idiot, right? Storage constraints for the mold, sure. Mold's massive, but mold's massive anyways. For the pre-preg itself, we have quite a few freezers. That's not an issue. Inconsistent consolidation pressure when autoclaves are not available. Yeah, you can have more vacuum ports. That's not that big of a problem. Yeah, wet
Right.
layup. Everything you said about wet layup is yeah. Yep. Um, yeah, all composites rely on environmental conditions. There's nothing we can do about that. Um, okay, cool. Yep, that's all. That's
Right.
all my
So
thoughts for
you
this.
mentioned a couple of things regarding that the technique skills required. Could you go into that a little bit more in depth? I want to update the documentation on that.
Yeah, so like the quality of vacuum bagging that you're doing has to be really high skill. And y'all haven't done a wet layup. Y'all haven't done a layup yet, which is very sad. Right? It's kind of the it tends to make members quit. Fair warning. Um, but like, yeah, like it still requires skill. You can't put too much tacking material down. How you place the fiber, it's now dry rather than being wet. So like you can have the towel can come off. Um, the vacuum bag, the bagging procedure is going to take way longer. You have to do a pressure drop test. If the pressure drop test fails, which it likely will, you now have to figure out why. And that is not fun. All of these require some technique and skill, and they're things we've never done. So they can take and it takes time, right? An infusion is maybe the longest process out of all of them. Infusion
Right.
will take the longest because you have to monitor the epoxy. So if someone fucks up and they mix material and they put it in a bucket that had epoxy already in it, and now it starts to flash crystallize, all of a sudden you've screwed up your entire infusion. If you take too long or you go too fast or you don't put enough epoxy in or you put too little epoxy in, it's not always a great process. It's very much it's the method for if you don't have access to any other large oven equipment. Like the other teams that do large infusions do it for two reasons. Either it's because they don't have access to it or because they actually don't know what they're doing. And that's quite common for composites in the US, is a lot of people don't really know what they're doing. Um, so yeah. And it's not really, you know, cost effectiveness. It's yeah.
Oh, gotcha.
Repeatability, it can be. But repeatability is always going to matter on the quality of your tool. Can you reuse the tool again?
Right.
And
You
every
mentioned
process, all three of these processes are repeatable. Like the same way I lay up a flat plate, I use to lay up an under tray, I use to lay up a bodywork. The same way I use to make a pre-preg firewall, I use to make a pre-preg wing, kind of. I use to make a pre-preg side pod, I use to make a pre-preg under tray, I use to make a pre-preg monocoque. Doesn't change really. There's more advanced versions of the same skill, but it's all the same process, really.
okay. You did mention that no one has done this. Is that including the other sub teams or the other design teams? Because I've talked to Electric and they have been trying to spearhead this project since last year. I was wondering
They,
if we, hello?
sorry, go on.
I was wondering if um, I don't know if we can exactly like copy their formulation, not formulation, but copy their like process one to one because it is a pretty standard process. I was wondering if we could we could reach out to them to see how they do it and have a couple of their members, if they have done it, look over how we are doing the process and help us guide through it because that might address the skill factor issue that you're talking about or experience issue.
Little. That's more like what I'm thinking of, more of like a skill issue is like the vacuum bagging process itself requires quite a bit of skill to
Right.
do right the first time. Right? It's all about first pass quality, right? And so the likely chance you'll do it first time right is slim. Because y'all have never even done a test the first time or do it on a wet lab where it really doesn't matter that much, right? I don't know if Electric has done it. Solar might be the closest to having done it, and they have their team has a better understanding of a composite material as a whole compared to Electric. Electric really weirdly has lost a lot of its fundamental understandings of like practicum. It's never really had a great understanding of composites in the first place, anyways. Um, they just kind
Well,
of do
sorry,
and don't care about how much it costs.
I just wanted to say that we have the resin infusion kit like
That didn't
here.
do it.
So yeah, just for the sake of like getting our, I guess, feet in the water trying to do at least a couple of tests.
Yeah, do it.
So
Do it. But what I'm saying is just because you have the ability to do it, like we have the ability to make like the, forged SMC parts. We've done it. We've done it multiple times in the past. We can do it.
but if this is something
But we're
that
not doing it, right?
yeah, exactly. This is something we've tried to do in the past, and if you can use it for a part like under tray, then like there's no point in not trying,
Well, there's the possibility you could use it for part of the inner train. That's what we're getting at. What we're getting at is like, I'm not saying that you shouldn't. No, give it a go, right? Give it a go and see how it goes and how do you do it and what are the problems and blah, 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 right? Do it. But then when it comes down to the decision of being like, okay, well, do we use it for under tray? You do the cost analysis. You say, okay, well, how much is it going to cost to have a mold that is never going to leak? So it can't be a multi-part mold. It can't be of a crappy foam material. How do we make this mold, this huge mold that's good that we can use for resin infusion? And then the cost of the resin infusion material, because it's a lot of consumables, or it's a lot of things that are, not the part, right?
Mm-hmm. But it's just an
and
extra.
then how long is it going to take you to do it, right? And how long prep and everything. And then compare the cost and the time to pre-preg.
Yeah.
Because then the pre-preg is going to give you a better part. It's going to cost less. It's going to cost the same for the material. And you're just really comparing the cost of either an autoclave or a really big oven. Maybe finding a company like Harris Composites that might donate you time in their oven. Right?
Yeah. But to be able to do that, I think we need to first just try it out ourselves,
Yeah, no, I'm not saying that not try it out. What I'm just saying is like the conclusion that we came to in the past, the reason why we didn't even spend the money on the infusion kit is we noticed that the cost of tooling was too much. The cost of tooling and consumables was too much.
Yeah.
And the quality of part you were getting wasn't that high. Anyways, continuing on.
Right. Within this, the resin infusion is just vacuum-assisted resin infusion. It follows the same process that's typically outlined by Easy Composites. We're going to be using Easy Composites as our kind of our Bible in this one, as we do with most things. So we're going to watch the tutorial videos and implement it to the best of our ability. That's the solution. So yeah, vacuum assisted, it solves for the issues regarding wet layup, in the sense that yeah, it's going to actually be even distributed. It requires more skill for sure, considering that wet layup's kind of a fuck it we ball as opposed to the other one. So yeah.
I wouldn't define this as closed mold process. This is still an open mold process.
Gotcha. Okay.
Closed mold defines that the mold, like what you're molding, is entirely enclosed. Right?
Okay.
Like the also term for this also is VARTM, which is vacuum assisted resin transfer molding.
Okay. Sounds good. And the implementation, we're just, if anything, yeah, once again, we're going to be using Easy Composites as our tool guide for this development project. Hello?
Yep.
Okay. And this is more of a get our feet in the water kind of thing. And if there is any deliverables that we could see at the end of this semester, it would be that we would make the under tray. Yeah, we would implement the under tray. So we'd validate this process through the ways that we outlined below. And if anything, yeah, this should be a relatively straightforward process. I know it's complex in its steps, but we are able to implement this considering we have resources and not previous members, but members potentially in electric and or solar that we can reach out to should we not get the guidance that we hope to get from Easy Composites.
Your vacuum hoses, just make sure you don't use our current ones. Like they need to have some type of replaceable I don't care if resin gets in it hose
Oh, okay.
because you can't get resin in our ports. If you get resin in our ports, you destroy them. So you have
Right.
to use new, different ports.
Gotcha.
You also need to look at resin aeration during the mixing process.
Okay.
I've
Writing
known
that
that
down.
I think that's been an issue I've heard before. Yeah. We used to have, I thought we had a resin depressuring pot
I think we do. It's in
in
pickle.
pickle. And
Yeah.
it's like
We
ancient and it was Solars from like 20 years ago or something.
yeah.
But yeah, it's
I was just going to ask about that.
yeah, luckily
Have
the nice
you?
thing with infusion is you remove void control. Void content no
Mhm.
longer becomes an issue. Actually, comically enough, infusion is phenomenal for monocoque, for the mold itself, for the tooling.
I can imagine. Yeah.
Well, because you have no voids.
Hmm.
You basically near guarantee voids, especially if you use resin that has been degassed.
Yeah.
Okay, continue on. Unless anyone else has anything. No, cool.
I should.
Yeah. Pretty straightforward. So, like mentioned, because Charles brought it up, I think we're gonna start with first test panels, and then from there we're gonna start working on low risk components, and then our final project will probably be the under tray. Um, and then from there we could run. I don't know how we would run tests on it. Looking to Wesley for the guidance on that. Within like comparing pre-preg to the resin infusion or VARI, how would we compare them and make that decision? Okay, we want to go with pre-preg as opposed to the project that we did with VARI.
In what? Compare in what way?
Comparing as in we wanted to see which one would be the more ideal candidate for the actual car itself.
You can do material testing on the infusion material to
Okay,
get like what is its modulus and what is its failure stress.
gotcha.
Then you can do then you look at like, you know, um how hard was it to do? You know, how long did it take you?
Yeah,
And then you look at the mold. So how long did it take to do the mold? How much prep did you have to do on the mold? How much did the mold cost? And then you do consumables. So for pre-preg, you have peel ply and you have breather and you have the vacuum bag. And then for infusion, you have the like 13 things that you need that are basically
yeah.
all consumable, right? Um, so yeah. Yeah.
All right, yeah. And so yeah, the design work that's been done so far is writing the initial document. I'm gonna update it with all the feedback that I've gotten today, and then we have bought easy the resin infusion starter kit. So
Yeah.
at one point we will get like I think as the semester starts, we will get me and Amaya will plan out a time to start working on that, and then yeah,
Yeah.
that's
After doing a couple tests, you'll really figure out like how much this is going to cost.
yep,
And then you can look at that versus pre-preg and then be like, okay, maybe resin infusion for an under tray is maybe $100 or $200 cheaper, but then we don't have to buy cables. So there's, 60 to 80 bucks. And we can do more kind of crazy insert stuff on for under tray mounting, which is a plus, and then the under tray is lighter.
yep,
So is the team willing to spend, what is probably going to be $100 or $200 on 5 to 8, maybe 10 pounds worth of weight savings?
yeah,
And
gotcha.
then the answer is going to be yes. because we have spent more money on less. Go look at rims. So, uh, yeah, yeah,
Awesome.
that was a conclusion we came to. Um, yeah, but y'all should still do it. It's a good thing to learn. It's not like it's, all the like most prototype engineering, especially in automotive, they all use resin infusion.
Gotcha. Yeah.
Alrighty. Thank you for that shit.
Yep, no worries.
Just going over a little bit of manufacturing. I know we focus a lot on manufacturing in the actual assemblies. Um, Mostly just on timeline. So this is from the LHR Composites timeline that Utsav, Ryan, and I made last summer. Of course, we made that with the intention of starting testing last year and also having access to facilities. We have not gotten full complete access back yet. We're hoping to very, very soon and hoping to hit the ground running as soon as we do. With that being said, a quick estimate for foam machining from Andrew Thorne is around 1200. I'm going to speak to him soon about setting up that timeline and confirming materials and scheduling. When it comes to the other components, we're testing out a couple of things here and there. Like, of course, the 3D printer components. I'm actually sitting next to them right now. I know Wesley mentioned like the surface quality might not be the best. I do think it's pretty good. Definitely not as good as aluminum for sure, and not as good as or as easy to use as epoxy tooling board would be. That was the original end goal. Hopefully next year though now, I guess. Also considering MDF, what if that's a possibility to make a better front wing than 3D printing is? We're contemplating a couple of things. Love to hear your thoughts on that and what you might think is something we should definitely not try, or we think something we definitely should try. Things like that.
Um, I wouldn't go NDF because I think it will require a lot more work.
Mm,
And it's not really standard. And if you're going to make it like MDF makes sense if you're like gonna do the MDF to make a fiberglass mold and then then put it in the oven. But that's a lot of work, and I'm lazy, so I would just go with tooling board or aluminum. And like machine them for like small stuff. It doesn't really make any sense if it's going to go
mm,
pre-preg. Tooling board's really not that expensive in small portions. In very large portions, it is.
mm.
It's a big upfront cost. Yeah, what's the status on Celine, Sawyer, Peterbilt?
Unfortunately, getting ghosted by everyone. Um, but as the
Is
semester
the
does start back
other
up,
two teams also being ghosted, or what's going on there?
I believe so. Amaya, I think we
Yeah,
spoke with Advait.
no, I didn't. I didn't speak with Advait. I spoke to the electric like composites. Um,
Oh, Anya.
so yeah, Anya, and then she said that they've been getting ghosted by Peterbilt as well. So
Okay,
it's,
I'll message the peeps.
this was a couple weeks ago. So I haven't asked again, but I can
Yeah,
message.
ask again, and then if not, then maybe I'll email them.
Okay.
And then, has anyone talked with Solar about their Sawyer and it being a no-no? Anyone?
I have not.
Cool. Have you discussed with Celine?
I was actually thinking about sending them a like Happy New Year's message and reaching out to
Send a
them.
Happy New Year's message, reach out, and discuss with them about how we together can both make what happened last year not happen again.
Hmm.
And if they have time for us. Like
Yeah.
maybe rather than them buying the foam and then handing us the money and then handing us like how much it costed them. The only reason we did that was because they probably get a discounted price, which they do because they're a big supplier, right?
Hmm.
Um, that rather than that, we reach out to the company, we get the foam delivered to their place in California, and then it gets shipped here, right? Or he might have his CNC robot up and running there in Round Rock,
Hmm. Yeah.
right? So, but don't just because they were shit last year doesn't mean they will be shit again. And your current situation is shit. So
Yeah. Doesn't hurt to try.
no harm in trying. No harm in having a backup, but no harm in trying.
Yeah. Awesome.
You'll get better parts out of it that way
Hmm.
than going through chlorine.
Yeah.
Just 4 inches is
Alrighty.
not enough.
So with that, I want to say thank you to everyone that came. I know this is quite the design review, just under 5 hours. Thank you to alumni, Wesley, Leo, Charles. Really appreciate the advice. Genuinely, I learned a lot more than I ever thought. I know I'm a stubborn person, and I came into this design review thinking I had it all figured out. Definitely did not. And thank you guys for the advice. Of course, Ryan and Leo, thank you for hosting this, right? And leading this like the team. And of course, all the composites members. Um, Not only thank you guys for congratulations, like it's been an amazing design review, a design season. The first time of at least my tenure here at UT that I've seen like FEA being done to this level within the system. I remember Wesley teaching me a rod sim in FEMAP one day over Zoom, over a Discord call, and we're doing a lot more things we did then. So congratulations to y'all. Happy New Year's. Let's make this an amazing 2026. And looking forward to the amazing manufacturing testing season with y'all.
Yeah, thank you guys so much. Thank you, Wesley, Leo, obviously Leo and Ryan. You guys are awesome. Yeah, thank you so much for everyone who came. Really appreciate it.